You've likely come across the headlines: an interstellar comet exhibiting strange chemistry, with a Harvard astronomer boldly suggesting extraordinary possibilities. But there's more beneath the surface, and some critical details are often left out. In less than a month, the object known as 3IATLAS will slip behind the Sun for a full 4 weeks, a total observational blackout. During that period, every telescope on Earth will be unable to monitor it, rendering us blind to any maneuvers or anomalies. If Avi Loeb's hypotheses are correct, this object could perform subtle course adjustments during that time, and we would have no way of detecting or confirming such actions in real time. Examining its trajectory, 3IATLAS traces a path almost perfectly aligned with the plane of the solar system, deviating only by about 5 degrees. This is unusual because most objects passing through our neighborhood, especially interstellar visitors, arrive from a variety of random angles, often tilted at steep inclinations relative to the ecliptic, the flat disk along which Earth and the other planets orbit. Instead, this object's orbit is nearly flat against that plane, suggesting a level of organization that defies expectations for a random interloper. Further compounding the mystery is its chemical signature. The ratio of carbon dioxide to water vapor in its coma is approximately 8:1, a stark contrast to what we would anticipate, where water should dominate as the primary volatile. Additionally, it appears to be venting nickel without any detectable iron, a phenomenon that current models struggle to explain. Its journey takes it past Mars, then the Sun, and finally Jupiter, following what looks like a precise sequence of waypoints, akin to a carefully planned flight path rather than a chance encounter. But what Avi Loeb is really emphasizing extends beyond the specifics of its trajectory and chemistry. It touches on a fundamental question. Can we seriously investigate anomalies that challenge our understanding? Can we sit with uncertainty, resisting the impulse to dismiss or panic? Right now, we are indeed struggling. Our teams have spent days scrutinizing every observation, spectrum, and model related to this object. What makes this case truly different, and why does the upcoming 4-week period when the object vanishes behind the Sun hold such significance? Because whether 3IATLAS turns out to be the strangest comet we've ever seen or something entirely different, our response now will determine what we learn or fail to learn. This moment is a litmus test for our scientific readiness and our capacity to confront the unknown. Let's delve deeper into these issues, but first, if you're interested in analysis that explores beyond surface headlines, I encourage you to consider the significance of what's unfolding. Reflect on where you're listening from tonight and consider, are we truly prepared to face phenomena that might defy our expectations? Or are we just exposing how unprepared we are? Chapter 1. The Unusual Path of 3IATLAS. Avi Loeb points out that 3IATLAS isn't following a haphazard path. Instead, its trajectory strongly suggests a deliberate plan. When the survey telescopes in Hawaii detected this object in September of 2024, the initial reaction was one of alarm and curiosity. Most comets entering our solar system arrive from distant random directions, their orbits tilted at a wide range of angles relative to the ecliptic, the flat plane where most planetary orbits lie. These interstellar visitors are usually like meteors streaking across the sky at bizarre angles, on unpredictable trajectories. In stark contrast, 3IATLAS's orbit reveals an inclination of roughly 175.11 degrees. To clarify, this indicates a retrograde trajectory, meaning it moves opposite to the direction of our solar system's planets. Yet remarkably, it is only about 5 degrees off the ecliptic plane. For an interstellar object, which should arrive from a random direction, such an organized, near-flat orbit is extraordinary. Avi Loeb, a Harvard astronomer known for his candid assessments, bluntly states that this resembles more like a flight plan than a random plunge. This isn't mere speculation. The data underpinning this observation is concrete. The precise inclination, along with its trajectory passing close to the Sun, Mars, and Jupiter in a sequence that appears carefully orchestrated, raises profound questions. It suggests a level of planning or intentional guidance that challenges our assumptions about natural interstellar arrivals. In the coming sections, we will explore what makes this object so peculiar, its chemistry, its trajectory, and what they could imply, whether natural or artificial. But for now, the key takeaway is that 3I-ATLAS's path isn't random. It appears to be carefully designed, prompting us to reconsider what we thought possible in the realm of interstellar visitors. Its eccentricity measures around 6. This is no typographical error. In the realm of orbital mechanics, an eccentricity of exactly 1 signifies a parabolic escape trajectory from the Sun, indicating the object is just on the verge of leaving the solar system's gravitational influence. Any value exceeding 1, therefore, signifies a hyperbolic trajectory, meaning the object originated elsewhere and is now making a swift departure, having come from interstellar space. An eccentricity as high as 6 is extraordinary. It's as if the object arrived at a cosmic gathering doing 90 miles per hour through the front door. An unmistakable sign that it did not originate within our solar neighborhood. It came screaming in from interstellar depths, traveling with enough velocity to leave no doubt about its extraterrestrial provenance. This conclusion was not drawn by a single team or a lone observer. Multiple research groups around the globe confirmed its hyperbolic path. The first to spot this visitor was the ATLAS survey in Hawaii. Recognizing its unusual trajectory, they promptly reported their findings to the Minor Planet Center, prompting observatories worldwide to mobilize. From the Pan-STARRS telescopes in Canada to facilities in France and across Hawaii, and many other professional observatories across different continents, the same startling truth was reaffirmed. This object was real, it was here, and it was heading straight for the Sun. The impending closest approach, perihelion, will occur on October the 29th and 30th in the year 2025, less than a month away. At perihelion, 3I-ATLAS will be approximately 0.96 astronomical units from the Sun, placing it well within the orbit of Earth. Its nearest point to our planet will be about 1.8 astronomical units, roughly 168 million miles, far enough to pose no impact threat according to NASA and ESA. They have been unequivocal in their assessments, emphasizing that the celestial geometry simply does not favor an impact scenario. Yet, as straightforward as that statement may be, the path of this interstellar visitor presents other intriguing opportunities. The trajectory offers a sequence of critical windows that could be exploited for observation and study. On October the 3rd, 2025, the object will pass relatively close to Mars. The proximity is sufficient for the European Space Agency to plan targeted observations, with the Mars Express Orbiter and the Trace Gas Orbiter prepared to aim their instruments at it, an event just days away from now. Following this, the object will reach perihelion, the point of closest approach to the Sun. But what truly captures attention is what happens next. On March the 16th in 2026, the object will pass within 0.358 astronomical units of Jupiter, about 33 million miles from the largest planet in our solar system. This sequence, Mars, Sun, Jupiter, provides 3 distinct vantage points, each offering unique observational opportunities that could reveal crucial details about its nature, composition, or potential artificial characteristics. All these observations are further complicated by the phenomenon known as solar conjunction. During this period, the object will pass behind the Sun from Earth's perspective, creating a 4-week observational blackout starting in late October. During conjunction, neither the Hubble Space Telescope nor ground-based telescopes will be able to track or image it. Even the James Webb Space Telescope will face limitations. If one were designing a course through the inner solar system with the aim of minimizing detection or observation opportunities, this window would be nearly ideal, a perfect cloak during the object's most active phase. From a purely scientific perspective, honesty demands acknowledgement that a low orbital inclination does not automatically imply intent or artificial origin. Interstellar objects are believed to be ejected from their parent planetary systems during formation, often from the dense disk-shaped regions where planets coalesce. Such ejections could naturally favor trajectories that align with the plane of their birth systems, which might coincidentally be aligned with our ecliptic plane. Additionally, our detection biases come into play. Telescopes are more sensitive and more frequently pointed at the plane where most objects pass through, further increasing the likelihood of discovering interstellar visitors with low inclinations. In sum, while the high eccentricity and trajectory of this object are extraordinary, they do not necessarily point to artificial engineering. Instead, they highlight the importance of understanding natural processes and recognizing our observational limitations, especially when the geometry of its path aligns in such a way that key observational windows are deliberately or coincidentally obscured. But here's the unsettling truth that often keeps astronomers awake at night. In all of human history, we have confirmed only 3 interstellar objects passing through our solar system. The first, designated 1I Oumuamua, arrived unexpectedly in 2017, distinguished by its highly inclined, steeply tilted orbit and an unusual acceleration that defied easy explanation, challenging our understanding of natural physics. The second, known as 2I Borisov, appeared in 2019 and initially appeared to be a typical comet, exhibiting the familiar characteristics of icy bodies born in other star systems, yet it arrived from interstellar space, confirming its exotic origin. Now the third, labeled 3IATLAS, enters our awareness, following a peculiarly flat trajectory that aligns with an unusual timing. Its perihelion, the closest approach to the Sun, coincides precisely with the period of solar conjunction, when our observatories are effectively blind, unable to monitor its progress. What makes 3IATLAS even more intriguing is that it isn't just the trajectory or timing alone that raises eyebrows. It's the compelling combination of multiple factors: the orbit's shape, the precise timing of its closest approach, and the geometry of its path, all woven into a pattern that seems almost deliberately crafted. Avi Loeb, the prominent Harvard astrophysicist, describes this trajectory as a rail-flat glide path, akin to a perfectly straight level line that culminates in a solar eclipse. From a strategic perspective, if an entity, be it an intelligent civilization or otherwise, aimed to approach the inner solar system while avoiding detection, this would be a near-optimal route, carefully designed to minimize observational opportunities. Humans are naturally pattern-seeking creatures. We see faces in clouds, faces in shadows, and often attribute agency to randomness, an innate trait that helped our ancestors survive in a world full of unpredictability. While this tendency is invaluable for survival, it also urges caution in interpreting the universe's signals. The universe does not owe us the courtesy of making sense. Coincidences do occur, and just because something appears improbable doesn't mean it's impossible. To illustrate this, consider this thought experiment. Imagine standing in a vast field and someone throws a dart from a mile away. Miraculously, the dart lands within inches of your feet. Your instinct might be to ask, was that a coincidence, or was it intentional? 3IATLAS is that dart. We are beginning to question whether it was a mere chance or the deliberate aim of some unseen hand. The most critical window for observing any anomalies, The moment when we might detect unexpected behavior, course adjustments, or signs of artificial origin, is fast approaching. During the period of solar conjunction, when the sun's glare renders our observatories blind to the object's whereabouts. This silence before the sun is a period of intense anticipation, as any activity or maneuver by the object, whether natural or otherwise, would most likely happen during this window when our instruments cannot see it directly. But before we plunge into this blackout phase, it's essential to understand what astronomers have already observed when they meticulously aimed their most advanced instruments at this visitor. Because the optics and chemical composition of 3IATLAS seem even stranger than its trajectory suggests, some features hint at anomalies, glowing phenomena that resemble headlights. In Chapter 2 of this unfolding story, we explore these headlights in the dark and the puzzling nickel anomaly. On July 21, 2025, the Hubble Space Telescope directed its sharp, sensitive eye toward 3IATLAS, capturing the clearest images we have to date. These images reveal that the object resembles a comet, complete with a nucleus, the solid core, whose size estimates range broadly from approximately 320 meters to 5.6 kilometers. This wide range exists because Hubble's observations focused on a fuzzy, active body enshrouded by dust and gas make precise measurement challenging. Nevertheless, the critical takeaway is that 3IATLAS is small enough to be naturally formed, an icy chunk that could have originated in the cold outer reaches of another star system, and yet large enough to hold significant structural implications. The images also show a sunward-facing dust plume and a faint anti-solar tail, the classic hallmark of a comet being warmed and baked by solar radiation. As the nucleus sublimates, gas and dust are carried away, forming a tail pushed by solar pressure, creating the unmistakable silhouette of a body actively shedding material. Subsequent observations by the Gemini Observatory revealed an even more extended anti-solar tail emanating from the object, stretching far behind it as it travels through space. This observation suggests that the object is actively outgassing, displaying behaviors characteristic of a dynamic moving body rather than a passive icy relic. Its tail is not a mere remnant but a sign of ongoing material ejection, reinforcing the idea that it is in a state of activity. However, when Avi Loeb examined the same set of data, he interpreted certain features differently. He identified what he termed a forward glow, a luminous region positioned on the sunward side of the object. This bright directional emission does not quite match the typical morphology of a cometary coma, which usually appears more diffuse and symmetrical. Instead, Loeb proposed that this glow resembles headlights, an active, directed emission rather than passive scattering of sunlight by dust particles. To him, this suggests that the object might be actively emitting or glowing toward the sun, potentially indicating some form of internal or external energy process at work. Loeb was careful to clarify that his observation is an interpretation, not an established fact. Mainstream astronomers, meanwhile, interpret the same features as a dust plume, consistent with the tail observed by both Hubble and Gemini, which show clear signs of tailing activity resulting from outgassing. The question of who is right hinges on which aspects of the data one emphasizes. The tailing activity itself is undisputed. Both sets of observations confirm that the object is shedding material and creating a tail. What Loeb points out, however, is the distribution of brightness across the object's surface and immediate vicinity. In a typical comet, the glow around the nucleus tends to be relatively symmetrical, shaped by the solar wind and radiation pressure acting on dust and gases. This symmetry results in a roughly uniform brightness distribution. Loeb notes that in this case there is an asymmetry. More emission appears to be directed toward the sun than would be expected if dust scattering were the sole cause. Such an asymmetry could arise from various mechanisms. For instance, it could be due to dust jets preferentially pointing sunward, possibly influenced by the nucleus's rotation or surface features that concentrate outgassing in a specific direction. Alternatively, Loeb speculates it might be evidence of active thermal management, an engineered process whereby the object deliberately vents material to regulate its temperature as it approaches the sun. Having discussed this intriguing brightness asymmetry, let us momentarily shift our focus to what the James Webb Space Telescope uncovered. Unlike visible light telescopes, JWST operates primarily in the infrared, which allows it to analyze the chemical composition of the gases surrounding the object in unprecedented detail. On August 6, 2025, JWST pointed its spectrometers at the comet and conducted a thorough analysis of the gas cloud enveloping it. The findings, released on August 25th, immediately sparked buzz across the planetary science community. What made these results extraordinary was the composition of the gases. JWST detected an unusually high abundance of carbon dioxide relative to water, specifically a ratio of approximately 8 parts carbon dioxide to 1 part water. To put this into perspective, most comets are predominantly composed of water ice, with other volatiles like carbon monoxide and carbon dioxide present in secondary amounts. When a comet approaches the sun, the water sublimates first, forming the characteristic coma and tail, with carbon dioxide often acting as a lesser component. A ratio of 8 to 1 indicates that this comet is venting 8 times more carbon dioxide than water. Such a composition is rare and places this object squarely in the what the heck category of cometary science. While some comets with unusual volatile mixes have been observed, such an extreme ratio is highly atypical and raises questions about the object's formation and thermal history. Adding to the intrigue, the Space Telescope SphereX, designed to map the sky in infrared wavelengths, also observed 2025, focusing on this same object. Its measurements revealed an enormous carbon dioxide coma, extending at least 348,000 kilometers from the nucleus, nearly the distance from Earth to the Moon. This vast envelope of CO2 indicates that the object is wrapped in a thick, expansive cloud of this gas, far larger than many planetary magnetospheres. Crucially, SphereX did not detect comparable amounts of water or carbon monoxide in the same observations. The dominance of carbon dioxide is consistent across multiple instruments, suggesting that this is not a measurement anomaly but a genuine feature of the object's composition. This peculiar chemical signature, venting copious amounts of CO2 with relatively little water, defies the expectations set by natural comet formation, which generally results in a composition dominated by water ice that sublimates at closer distances to the sun. These chemical peculiarities, such as the vast CO2 envelope and the high CO2 to water ratio, prompt fresh questions about the nature and origin of this interstellar visitor. Are we observing a natural object formed under unusual conditions, or does this celestial object is shrouded within an expansive envelope of carbon dioxide, forming a bubble that surpasses the size of most planetary magnetospheres, an astonishing and unusual feature. And here's the intriguing part. Observations from the SphereX Space Telescope, which specializes in infrared mapping, did not detect comparable amounts of water vapor or carbon monoxide in the same epoch. This persistent carbon dioxide dominance isn't merely a fluke or an anomaly confined to a single measurement. Rather, it has been corroborated across multiple observations and instruments, reinforcing its significance. But why does this matter so much? The reason lies in how it challenges our conventional understanding of comet formation. In the cold, distant regions of star systems, water ice is typically plentiful. It condenses out of the primordial nebula into icy bodies, forming the icy core of comets. Carbon dioxide, too, condenses at these frigid temperatures, but usually under different conditions, at slightly lower temperatures and in different zones within the protoplanetary disk. A comet exhibiting a ratio of about 8 parts carbon dioxide to 1 part water, therefore, suggests it originated in a very particular thermal environment. It might have formed near a so-called CO2 snowline, the boundary where carbon dioxide transitions from gas to solid, or perhaps its surface underwent extensive radiation processing during its time in interstellar space. This radiation could have effectively sealed off the water ice beneath a crust of carbon dioxide ice, preventing it from sublimating or escaping in the current epoch. On a more speculative note, if you're inclined toward more exotic explanations, consider that carbon dioxide is an excellent working fluid. It sublimates, transitions directly from solid to gas at lower temperatures than water, making it easier to manipulate in thermal management systems. If one were designing a passive cooling system for a spacecraft approaching a star, carbon dioxide would be a prime candidate due to its thermodynamic properties. It can efficiently carry away heat without the need for complex machinery, simply venting as it sublimates under solar heating. But the chemical peculiarities don't end there. Enter nickel. The Very Large Telescope in Chile, equipped with the ultraviolet spectrograph, UVS, and X-shooter spectrograph, detected emission lines from neutral nickel atoms, designated as NE1 in the coma of 3IATLAS at surprisingly great distances from the nucleus. Nickel emissions in comets are not unheard of. They are sometimes observed, but generally faint, typically associated with vaporized metal-bearing dust grains that are heated intensely by the sun near the comet's nucleus. What's perplexing here is the magnitude of nickel detected and, remarkably, the near absence of iron emissions. In the cosmos, iron and nickel are often found together. They are abundant products of stellar nucleosynthesis, the process by which stars forge elements in their cores. In natural rocky or metallic bodies, these two elements tend to appear in tandem, rarely with nickel present without iron. Yet in 3IATLAS we observe a scenario where nickel lines are prominent, but iron lines are weak or altogether missing, an unusual and telling anomaly. How might this be explained? One plausible natural mechanism involves organometallic compounds, molecules where metal atoms bond with organic carbon chains. Nickel is known to form stable carbonyl compounds, such as nickel tetracarbonyl, which are volatile and can sublimate at relatively low temperatures. Under ultraviolet light, these molecules can break down, releasing nickel atoms that glow when excited by sunlight. Iron can undergo similar chemistry, but the pathways and conditions are different, and under certain circumstances, nickel might be preferentially released over iron. While exotic, this chemistry falls within the realm of known processes. In late September of 2025, scientist Avi Loeb highlighted what he termed extreme nickel production, as 3IATLAS moved from approximately 3.14 astronomical units to about 2.14 astronomical units from the Sun. He observed a delay in the emergence of iron emission lines relative to nickel, and suggested that this could indicate a form of non-thermal or even engineered heating, possibly a controlled release of materials rather than passive sublimation driven solely by solar radiation. Such a process might imply some form of internal or artificial mechanism selectively releasing nickel, hinting at a possible engineered origin rather than a purely natural one. In essence, this chemical puzzle, marked by an enormous envelope of CO2, the anomalous absence of water and carbon monoxide, and the peculiar nickel emissions, poses profound questions about the true nature and origin of 3IATLAS. Is it a naturally formed comet born in an unusual environment, or could it be something more engineered, a probe or craft designed with specific thermal and chemical properties? The evidence so far suggests that we are dealing with an outlier, an object that defies easy classification within our current understanding of cometary physics and chemistry. This remains a hypothesis, not a confirmed fact, yet it is one that can be systematically tested. If, as the comet approaches the Sun and its environment heats up, iron emission lines begin to appear, that would lend support to the idea that the observed phenomena result from natural organometallic processes. Such a development would align with known chemistry and physics, indicating that the unusual emissions and behavior could be explained without invoking artificial origins. Conversely, if iron remains absent or if the ratio of nickel to iron continues to be inexplicably skewed, significantly outside the expectations of natural processes, then the natural explanation becomes increasingly strained, raising questions about the object's true nature. To synthesize what we have observed so far, the interstellar visitor designated as 3IATLAS exhibits several peculiar features that challenge straightforward classification. First, there is a potentially asymmetric sunward-facing glow, an interpretation by Loeb suggesting a directed emission, perhaps akin to headlights rather than passive dust scattering. Second, it displays an extraordinarily high ratio of carbon dioxide to water, measured at approximately 8:1, placing it among the most extreme volatile compositions ever detected in a comet. Third, the object is surrounded by an enormous coma of carbon dioxide, extending nearly as far as the Earth-Moon distance, yet detections of water or carbon monoxide remain minimal. Fourth, spectral analysis reveals strong nickel emission lines without a corresponding presence of iron, an unusual chemical signature that hints at exotic chemistry or atypical heating mechanisms. Individually, none of these features are impossible within the bounds of natural phenomena. Nature can produce a wide array of outliers. However, the confluence of all these anomalies in a single object forms an outlier among outliers, defying simple categorization. This has led to the emergence of two primary competing models. The first posits that 3IATLAS is a natural comet, albeit one with an extraordinary formation history, possibly originating in a cold, remote region of its parent system or having undergone unusual radiation processing that accounts for its exotic chemistry and behavior within known physics. The second model suggests that 3IATLAS is something artificial, a probe or craft utilizing solar thermal energy for power or propulsion, actively venting gases such as carbon dioxide as part of its thermal management, and outgassing nickel-bearing materials as incidental byproducts of its operations. Currently, consensus remains elusive. No peer-reviewed explanation has yet emerged to reconcile the nickel-ion decoupling phenomenon, and the existing data set continues to challenge our conventional frameworks. We are racing against time, as the object will soon slip behind the Sun, ending our direct observational window. The critical question hangs in the air. Are we witnessing the universe's strangest comet, or are we observing signs of technology? Whose technology, and from whom? This is where the concept of the Loeb scale becomes invaluable. The Loeb scale offers a structured framework for quantifying how bizarre an object appears and whether its features cross into the territory of artificiality. When dealing with interstellar objects, rare visitors from distant star systems, such a scale is essential. Without it, we risk merely shouting our opinions into the void, unable to gauge the significance of anomalies with any objectivity. The Loeb scale and the spectrum of technology. Imagine yourself as a detective unraveling the mystery of a break-in. You would rely on evidence evaluation, fingerprints, motives, opportunities to build a case. In astronomy, especially when confronting objects that might be artificial, we need a similar system for assessing how unusual the data truly is. Enter the Loeb scale, also known as the Interstellar Object Screening System, or IOSS. This is a classification from 0 to 10, proposed by Avi Loeb, designed to rate the likelihood that an interstellar object is of artificial origin. 0 signifies a completely natural object, nothing suspicious, fully consistent with known physics and chemistry. 10 indicates a confirmed artificial object, beyond any reasonable doubt, a relic or craft engineered by an intelligent civilization. Most of the scientific community operates within this framework, with the majority of objects falling somewhere in the middle ranges. The key lies in the features we observe. Some anomalies are compelling but not conclusive, and the scale provides a systematic way of weighing evidence. The most critical judgments occur in the middle of this spectrum from about 8 to 10. These are reserved for objects where strong, reproducible evidence of technology exists, such as narrowband radio signals engineering signatures in light curves that defy natural explanations, or direct imaging revealing structures that cannot be explained by geology or natural processes. To date, no object has officially scored higher than about 7 or 8 on the scale, and none have been conclusively identified as artificial. For example, the interstellar object Oumuamua, discovered in 2017, received a score of around 7, considered highly anomalous but not definitively artificial, primarily due to its unusual acceleration and elongated shape. The second. We're examining signals such as narrow-band radio transmissions, engineering signatures embedded within light curves, or the direct imaging of structural features that defy explanation through natural geological processes. To date, we have yet to identify an interstellar object that scores 8 or higher on our classification scale. We've never even come close. Conversely, at the other end of the spectrum, the second interstellar visitor, known as Borisov, comfortably resides near 0. Borisov appeared just like a typical comet, with a composition rich in carbon monoxide, indicative of formation within a cold molecular cloud surrounding another star. While its interstellar origin made it exotic by definition, its properties were entirely mundane in nature. Its score, therefore, is firmly in the natural category, and the best approach is to move along and focus on other objects. Then there's the first confirmed interstellar object, designated 1I Oumuamua. Oumuamua, the enigmatic visitor that keeps astronomers endlessly puzzled. Discovered in October of 2017, Oumuamua was the first interstellar object we identified passing through our solar system. And from the very start, it exhibited bizarre characteristics. It was elongated, tumbling unpredictably, and lacked any visible coma or tail despite passing remarkably close to the Sun. It also demonstrated a tiny but measurable deviation from a purely gravitational Keplerian orbit, an acceleration that suggested some gentle push from an unseen force. Natural objects like comets frequently experience outgassing, which causes such non-gravitational accelerations. But Oumuamua showed no signs of dust or gas emissions. It was a mystery wrapped in an enigma. Loeb famously proposed that Oumuamua could be a light sail, a thin reflective sheet propelled by the pressure of sunlight. Alternatively, some hypothesized it might be a fragment of interstellar debris or even a decommissioned probe, an artifact of extraterrestrial engineering. The mainstream scientific explanation leaned towards outgassing of an invisible substance, possibly pure hydrogen, that wouldn't produce a visible coma but could still generate thrust. In the context of the Loeb scale, an ordinal ranking system designed to gauge how anomalous an interstellar object might be. Loeb himself assigns Oumuamua a score of around 7. This indicates a highly unusual object that defies easy explanation but remains unconfirmed as artificial. The broader scientific community tends to rate Oumuamua somewhat lower, perhaps around a 3 or 4, acknowledging its peculiarities while favoring the natural explanation, albeit with some exotic, poorly understood physics lurking beneath the surface. So where does the object known as 3IATLAS fit within this framework? According to Loeb, Atlas is positioned in the high middle of the scale, not quite as extreme as Oumuamua, but distinctly more peculiar than Borisov. To understand its classification, let's dissect the factors that influence its score, starting with geometry. The low inclination, roughly 5 degrees off the ecliptic, is atypical for an interstellar visitor. While not impossible, such an inclination is statistically uncommon, which nudges the score upward. Next, consider timing. Atlas's perihelion, or closest approach to the Sun, coincides precisely with a solar conjunction, effectively creating a blind spot for Earth-based observations during its period of maximum activity. This coincidence, whether accidental or deliberate, adds another point to the anomaly tally. Turning to chemistry, the ratio of carbon dioxide to water stands at an extraordinary 8:1. While this ratio falls within the broad spectrum of natural cometary diversity, it sits firmly at the extreme end. The detection of an enormous CO2 coma by the Spherex Observatory accentuates this point, underscoring the significance of this chemical anomaly. Furthermore, the emission pattern of metals, specifically nickel without the accompanying presence of iron, poses a substantial puzzle. Standard cometary models cannot readily explain such a pattern. Organometallic pathways involving molecules where metals bond with organic carbon chains could account for some of this chemistry, but they are exotic and not well established in natural contexts. The delayed appearance or absence of iron lines, if iron remains undetectable even as the object approaches the Sun, would be particularly difficult to reconcile with natural heating processes. Finally, optical asymmetries, such as unusual brightness distributions or directional glows, further complicate the classification. When combined, these features create a profile that is not easily attributable to a natural origin, yet not definitively artificial either. In summary, Atlas exhibits a composite of traits: a low inclination orbit, a timing coincidence with solar conjunction, extreme volatile ratios, peculiar metal emissions, and optical asymmetries. Taken together, these factors suggest a score that falls somewhere in the high middle range, around 5 or 6. Making it intriguing enough to warrant close scrutiny but not yet conclusive of artificiality. This classification system, the Loeb scale, is inherently dynamic. As new data emerges and our understanding deepens, the score can shift upward if anomalies intends Loeb's proposition of a forward glow, an unusual luminous region on the sun-facing side of the object, remains a subject of debate among scientists. Should future observations confirm this phenomenon, it would strongly indicate directed emission, meaning the object could be actively controlling or radiating energy in a specific direction, rather than merely reflecting sunlight via passive scattering. Such a discovery would be profoundly significant, potentially shifting our understanding of the object's nature. Currently, the assessment of this anomaly based on available data places the object's status around a 5 or 6 on the so-called Loeb scale, a subjective but structured way to gauge the level of anomaly or artificiality. This puts the object in a category that is intriguing and warrants close scrutiny, yet not definitive proof of extraterrestrial origin. It's a scenario that invites curiosity and ongoing investigation but remains inconclusive at this stage. It's important to remember that the Loeb scale isn't fixed, it's inherently dynamic. As new data arrives, the score can fluctuate. For example, if the interstellar object, designated 3IATLAS, reemerges from behind the Sun's glare and displays a non-gravitational acceleration, meaning it moves in a way that cannot be fully explained by gravitational forces alone. This would elevate its anomaly score further. Such a deviation could suggest active propulsion or other forces at work, raising the suspicion of artificial origin. Moreover, if the James Webb Space Telescope, JWST, detects narrow-band emissions at specific frequencies, signals confined to particular wavelengths, that would be a substantial jump in the anomaly rating, possibly pushing it into the high 7s or even an 8. These narrow emissions often hint at engineered sources, perhaps deliberate communications or signatures of technology. Even more compelling would be follow-up observations revealing periodic brightness variations. If these fluctuations exhibit regularity, geometric patterns, or other signs that suggest deliberate design rather than random natural variation, that would be powerful evidence supporting an artificial hypothesis. Such findings could propel the object's score into the high 9s or low 10s on the scale, crossing into what might be considered definitive proof of extraterrestrial engineering. Conversely, if after the object reappears, its orbit aligns perfectly with natural physics, no unexplained accelerations, increasing water vapor as it warms, a carbon dioxide to water ratio returning to typical cometary levels, and ion emission lines emerging in expected patterns, the anomaly score would decrease significantly. It might settle around a 3, indicating that, although strange, the object's behavior is consistent with a natural, albeit unusual, comet. So, what would truly push this assessment toward a perfect 10? What we might call the smoking gun. It would require unambiguous evidence of artificiality that defies any known natural scenario. For example, the detection of a repeating radio signal, one that is not just noise but a deliberate pattern or coded message, would be a powerful indicator. The content of such a signal could be considered an unmistakable hallmark of intelligence, elevating the score to a 9 or even a 10. High-resolution imaging from a spacecraft intercept mission, such as a proposed Juno flyby designed for close-up observation, could also provide decisive evidence. If the spacecraft were able to resolve angular features revealing flat surfaces, modular structures, or other geometric features inconsistent with natural geology, this would be a definitive game-over moment, an unequivocal sign that we are not alone. It is crucial to approach this topic with scientific rigor and caution, especially given the ongoing media noise. NASA has explicitly stated that current observations are consistent with a natural comet, pending any contradictory evidence. The agency has also rebutted claims of alien probes making headlines, emphasizing that the data so far do not challenge the conventional understanding of cometary behavior. This conservative, evidence-based stance is appropriate. Extraordinary claims require extraordinary proof. Why do we continue to discuss this matter? Because the accumulating evidence, anomalous chemistry, peculiar trajectories, unexpected emissions, gradually diminishes the likelihood that this is a simple, natural object. It's not impossible, but it becomes increasingly less satisfying as an explanation. The upcoming solar conjunction, which will temporarily obscure our view, makes this period especially critical. When the object reemerges, the data we gather then will be pivotal to our understanding. As an attentive observer, you can monitor the evolution of the object's assessment by focusing on specific signals and measurements. For instance, analyzing its position relative to predictions based solely on gravitational forces can reveal residuals, tiny deviations that may suggest thrust or other non-gravitational influences. Spectroscopic measurements can track the composition of outgassed material, checking whether the carbon dioxide to water ratio remains atypical or normalizes. Variations in brightness and the emergence of emission lines can also provide crucial clues. Each of these indicators contributes to a comprehensive picture, helping to refine the anomaly score and ultimately our understanding of what this object truly is. Let's consider the question of whether the volatile composition of this interstellar visitor, known as 3IATLAS, changes in a manner that aligns with our expectations from natural solar heating, or if it remains anomalously unusual. Specifically, does the abundance of key gases like water and carbon dioxide evolve predictably as the object approaches the Sun? Or does it hold on to atypical ratios defying our models? Similarly, regarding its chemical signature, will iron finally become detectable as the comet warms and its surface undergoes thermal processing? Or does the dominance of nickel continue to perplex scientists? The spectral lines, those telltale markers revealing elemental presence, are crucial here. Does iron, often expected to emerge during the object's closest approach, finally show up? Or does the nickel emission pattern stubbornly persist, hinting at something more exotic or engineered? Beyond chemistry, the brightness fluctuations of the object offer another vital clue. As the comet rotates, as dust jets erupt, and as surface features respond to solar heating, does its brightness vary in a predictable, smooth manner? Or are there irregular, sudden spikes, bright flashes, or dips that suggest additional processes at play, perhaps activity driven by internal mechanisms or even artificial interventions? When the comet re-emerges from behind the sun, observers will examine its photometric profile closely. Will it display a steady, expected increase or decrease in brightness consistent with thermal models? Or will there be abrupt, unexplained changes indicating that something extraordinary has occurred? Perhaps a sudden release of material, a structural shift, or an unanticipated energy source. All these data points, spectroscopic, photometric, temporal, are testable, and that is the core strength of scientific inquiry. Predictions can be formulated based on models, measurements can be taken, and the universe itself will serve as the ultimate arbiter, confirming whether our hypotheses hold or need revision. Currently, 3IATLAS occupies a somewhat ambiguous position on what I call the lobe scale, a framework designed to organize our confidence levels regarding artificiality versus natural origin. It sits somewhere in the middle, anomalous enough to grab our attention, yet not so extraordinary as to outright dismiss the natural explanation. But with a critical observational gap on the horizon, an upcoming period during which our ability to monitor the object will be limited, our story remains unfinished. Data from orbiters around Mars, and potentially even a flyby of Jupiter, could provide pivotal insights. But until then, the story remains open. Before moving forward, it's important to address the issue of selection bias. Skeptics rightly argue that our tendency to focus on strange phenomena stems from the fact that they are, by definition, outliers. If thousands of interstellar objects pass through our solar system, most of them mundane, then naturally the one or two that seem peculiar will attract disproportionate attention. Their strangeness might simply be a matter of chance, not indicative of artificial origin. However, the counterpoint is compelling. We have only ever detected 3 interstellar objects so far, 3 in total, and 2 of those, namely Oumuamua and 3IATLAS, fall into the weird category. This is a tiny sample size, far too small to establish a statistical trend. It remains a curiosity, but a curiosity that commands our scrutiny. The lobe scale isn't a verdict, it's a conceptual tool, a way to quantify and organize our uncertainty, to evaluate how close or far an object is from natural expectations. The pressing question, then, is just how improbable this coincidence truly is. Can we, in principle, estimate the odds that a randomly arriving interstellar object would display this particular set of geometrical, temporal, and chemical characteristics? To explore this, let's delve into some probabilistic reasoning. Part 4. The mathematical improbability of coincidence. Imagine this. You're standing in the middle of a football field and someone on the moon throws a dart. The dart lands within 10 feet of your feet. Would you consider that a random event? Or would you start asking questions about aim, intention, or perhaps some underlying pattern? This thought experiment encapsulates the essence of trying to quantify the likelihood that the trajectory of 3IATLAS arrived as it did purely by chance, While the actual calculations can become complex rapidly, the core idea remains straightforward. How often would a random interstellar object approach our solar system with the specific alignment, timing, and chemistry we observe? Let's first address the geometrical aspect, the alignment with the ecliptic plane. The ecliptic is the thin, flat disk where Earth and most planets orbit the Sun. It's a relatively narrow slice through the three-dimensional realm of space. If interstellar objects approach from truly random directions, coming in from all possible angles, the probability that one would arrive within a mere 5 degrees of this plane can be approximated. Using basic spherical geometry, the chance that a randomly incoming object aligns within 5 degrees of the ecliptic is roughly 1 in 36. In other words, out of this calculation rests on straightforward spherical geometry, a fundamental principle that isn't inherently extraordinary, yet neither is it commonplace. Statistically speaking, if interstellar objects arrive randomly from space, we would anticipate roughly 1 in every 36 to 40 objects to approach our solar system with a low inclination similar to what we've observed. In other words, based purely on chance, about 1 out of every 36 interstellar visitors should fly in at a shallow angle relative to the plane of the solar system's ecliptic. However, the challenge lies in our limited observational record. To date, astronomers have confirmed only 3 such interstellar objects passing through our celestial neighborhood. With such a small sample size, it becomes statistically unreliable to determine whether the peculiarities of 3IATLAS are genuinely extraordinary or simply a rare event among the expected 36. It's akin to flipping a coin only 3 times and trying to infer whether it's biased or fair. Our data is simply too sparse for definitive conclusions. Next, consider the timing of this encounter. The perihelion, the point at which the object comes closest to the Sun, is predicted to occur between October 29th and 30th in the year 2025. This period coincides precisely with the start of what astronomers call a solar conjunction, a phase during which Earth's line of sight to the object is obstructed for several weeks. During conjunction, the object would be behind the Sun from our vantage point, rendering it essentially invisible with ground-based telescopes. Is this mere coincidence? Well, solar conjunctions are predictable outcomes dictated by celestial mechanics, geometric alignments that happen regularly as objects orbit the Sun. Any object passing near the Sun will at some stage be aligned on the far side of the Sun from Earth's perspective. The crucial question is whether the comet's most intense outgassing phase happens to coincide with this observational blind spot. For most comets, the highest activity occurs close to perihelion because solar heating drives sublimation, the process where ice turns directly into gas, at its peak. Therefore, it's somewhat expected that the comet's most lively period would occur during perihelion, which in this case overlaps with the period of solar conjunction. However, the fact that this conjunction lasts for an extended span of several weeks introduces a layer of suspicion, as if the timing was deliberately or coincidentally optimized. Now let's shift perspective. Suppose you were designing a mission to explore the inner solar system but wanted to minimize your chances of detection from Earth. What trajectory would you choose? Naturally, you would favor a path with a low inclination, meaning it stays close to the plane where most planetary and asteroid activity occurs, so as to avoid unnecessary crossing of densely monitored regions. You would also plan a perihelion passage on the far side of the Sun from Earth during the most active phase, reducing the likelihood of detection. Multiple close approaches to planets like Mars and Jupiter would maximize observational opportunities while maintaining a stealthy profile. Indeed, the trajectory of 3IATLAS appears to check these boxes. It approaches Mars on October 3rd, and its perihelion occurs during the late October conjunction, precisely when Earth's line of sight is blocked. Then it passes near Jupiter on March 16th, in the year 2026. Such a sequence resembles an intentionally designed itinerary, a carefully crafted tour through the inner solar system with multiple vantage points. This is where the statistical argument becomes less clear. We lack definitive priors, meaning we don't have sufficient background data to determine how frequently such arrangements occur naturally. Our knowledge of how many interstellar objects pass through undetected remains limited. Estimates based on the first confirmed interstellar visitor, Oumuamua, suggest that at any given time there might be roughly one detectable interstellar object within one astronomical unit of the Sun. Extrapolating further, this could imply thousands of such objects crossing our solar system each year, many too faint or distant to observe. If interstellar objects are common, then encountering a rare configuration like this would not be surprising at all. It's akin to rolling dice repeatedly. Eventually, you'll hit a rare combination purely by chance. Conversely, if interstellar visitors are exceedingly sparse, then witnessing one with such a peculiar trajectory and timing demands an explanation, one that perhaps hints at deliberate design rather than natural randomness. To illustrate, consider a mental exercise, what's known as a Monte Carlo simulation. Though I won't actually run one here. Imagine generating 10,000 random interstellar trajectories, each with varying inclinations, velocities, and orientations. The question then becomes how many of these randomly generated paths would satisfy all the specific conditions observed, namely, passing within 5 degrees of the ecliptic plane, reaching perihelion during Earth's solar conjunction, and approaching both Mars and Jupiter within a 6-month interval. Based on rough geometric probabilities, I'd estimate that somewhere between 1 in every 100 to 1 in every 1,000 of such randomly chosen trajectories would satisfy all these conditions. In percentage terms, that's the rarity of such an occurrence is clear, yet the statistical perspective suggests that if thousands of interstellar objects traverse our solar system each year, then encountering a few with these particular characteristics over the span of a century would be expected. However, the unsettling reality is that we are not observing a handful of such objects across 100 years. Instead, we are witnessing a solitary one, right now, and this object exhibits an unusual combination of traits that defy straightforward classification. Its chemistry is peculiar, and it emits metal signals in ways that are layered on top of an already perplexing orbital geometry. To understand the significance, let's compare this object, known as 3IATLAS, with the only other 2 confirmed interstellar visitors we've documented so far. The first, Oumuamua, had an orbital inclination of approximately 122 degrees, meaning it approached from a highly tilted angle relative to the plane of our solar system, known as the ecliptic. It entered steeply, passed through our neighborhood, and exited just as steeply, following a trajectory that was unmistakably misaligned with the typical plane in which most celestial bodies orbit. Yet Oumuamua also exhibited a mysterious non-gravitational acceleration, an anomaly that has sparked much debate and speculation as it hints at forces or phenomena beyond simple gravitational influences. The second interstellar object, Borisov, had an inclination of around 44 degrees, still tilted but less extreme than Oumuamua. Borisov's trajectory was also inclined, not neatly aligned with the ecliptic, but it behaved in a manner consistent with natural cometary activity. Its chemical composition appeared normal, with the expected presence of carbon monoxide, water, and dust. Volatile substances characteristic of comets formed around other stars. It was, in many respects, a standard interstellar comet, following the expected patterns of cosmic debris. What emerges from these comparisons is that we do not have a pattern of similar cases. Instead, each interstellar visitor seems to fall into a different category, Oumuamua was peculiar in one way. Borisov appeared quite ordinary. And now, 3IATLAS is exhibiting a set of strange features that belong to a completely different realm of anomaly. This diversity complicates any attempt to argue that all interstellar objects share a common nature or origin. This leads us naturally to the question: how could such a low-inclination interstellar object have come about through natural processes? One plausible scenario is that it was ejected from a planetary system during its formation phase. Planetary systems tend to be flattened disks, like our own solar system, so if an object was expelled within the plane of its original system, and if that plane happened to align with our ecliptic, then the resulting trajectory would naturally have a low inclination relative to the plane we observe. While the odds of such an exact alignment are not high, they are not zero. Coincidences do occur in the vast universe. Another natural possibility involves gravitational perturbations during its interstellar journey. Stars in their orbit around the galaxy sometimes pass relatively close to each other in cosmic terms. A close encounter with another star could alter the object's trajectory, bending or rotating its path into the plane of our solar system if the encounter occurred at just the right angle. Both scenarios, formation in a flat disk and stellar perturbation, are entirely plausible within the natural framework. They both depend on coincidences, yet such coincidences are part of the universe's normal workings, and they happen with some frequency over cosmic timescales. On the other hand, there is an alternative hypothesis: targeting. If we consider the possibility that 3IATLAS is an artificial probe, its trajectory might have been deliberately chosen to maximize exploration efficiency within our solar system. Such a trajectory, low inclination, timed conjunctions to evade observation, sequential flybys of Mars and Jupiter, aligns precisely with what an intelligently designed mission would aim to accomplish. From a purely engineering and mission planning perspective, this is exactly what you would plan. A route that minimizes detection risk while maximizing scientific return. However, the critical point, an honest assessment, is that with the current data we cannot reliably distinguish between these two hypotheses. The mathematics and observational evidence at hand are insufficient to definitively favor natural origins with lucky geometry or an intentional engineered trajectory. Both scenarios are consistent with the trajectory data, and neither can be conclusively ruled out. What could change this assessment? The answer is straightforward: more data. Specifically, additional interstellar objects observed over time would help establish statistical patterns. The more objects we detect and analyze, the better our understanding of their typical inclinations, trajectory ranges, and chemical compositions. Such data would allow us to refine the probability calculations and determine whether the low inclination of 3IATLAS is a rare coincidence or part of a broader pattern indicative of intelligent design. Until then, the current sample size, merely 1, simply isn't enough to draw firm conclusions about the true nature of this mysterious visitor. If the Vera C. Rubin Observatory's upcoming legacy survey of space and time begins its operations and proceeds to detect dozens, perhaps even hundreds of interstellar objects over the course of the next decade, it will establish a crucial statistical foundation for understanding these celestial visitors. With such a robust data set, scientists will finally be able to differentiate what constitutes a typical interstellar trajectory from what is genuinely unusual. We'll gain insights into the frequency of low-inclination arrivals, those objects that enter our solar system with orbits closely aligned to the plane of the planets. And thus, we'll be better equipped to determine whether the peculiarities observed in objects like 3IATLAS are anomalies or merely the first of many similar visitors we happen to detect. Until that extensive statistical baseline is in place, however, We remain confined to the limitations of small sample sizes, which inevitably lead to probabilities that are unsatisfying and often misleading. But I want to leave you with a reflection to ponder. Coincidences, especially those that occur at opportune moments or under seemingly convenient circumstances, tend to evoke a sense of discomfort. When an extraordinary event unfolds in a manner that appears well-timed and fortuitous, our instinct is to interpret it as not purely random, but as something intentional or engineered. Yet it's important to remember that rarity or even improbability does not equate to definitive proof of deliberate design. Events that have a 1 in 1,000 chance of happening are not impossible. They are, in fact, quite possible, and they do occur somewhere to someone at some point in time. The real question is, are we that someone? Did our civilization stumble upon the rare 1 in 1,000 interstellar object purely by chance, or is the exceedingly low probability itself a sign that something more deliberate might be at play? The answer remains elusive because the mathematics alone cannot provide certainty at this stage. However, the passage of time can, and that's where the upcoming weeks become critical. In less than a month, 3IATLAS will disappear behind the sun, plunging into a period of silence from our vantage point, an interval during which we will be effectively blind to any further developments. If during this blackout window the object alters course unexpectedly, or if concrete evidence of artificiality emerges, that time period, this silence before the sun, will be the most consequential. It is in this moment of observational darkness that the universe might reveal whether this visitor was a natural comet or something engineered. This leads us to the next chapter, the silence before the sun, a phase fraught with tension and anticipation. There is a particular kind of suspense that stems from knowing that you are about to lose sight of something significant. It is analogous to the sensation of watching a car disappear around a corner just as you notice its erratic driving. An unsettling feeling that you cannot follow, cannot track, and can only hope that when it reappears, everything remains as expected. 3IATLAS's journey into this cosmic blind spot is imminent, and it will remain hidden from view for weeks. Let me take you through the timeline and the geometric considerations because this is where the stakes become tangible. The closest approach to the sun, perihelion, will occur on October the 29th and 30th of 2025. At that point, the comet will be at approximately 0.96 astronomical units from the sun, inside Earth's orbit, and subjected to intense solar radiation. For a natural comet, this period marks the peak of outgassing activity. Sublimation of ice, eruption of dust, and the formation of a bright coma and tail reaching its maximum extent. Simultaneously, this is when solar conjunction begins. From our perspective on Earth, 3IATLAS will pass behind the sun. Not literally in an eclipse, but close enough in angular separation that the sun's overwhelming glare will completely obscure it. Ground-based telescopes, those relying on visible light, will be unable to observe the object without risking damage or receiving only useless data. The Hubble Space Telescope, with its strict sun avoidance angles, cannot point within approximately 50 degrees of the sun. Similarly, the James Webb Space Telescope, stationed at the Lagrange point L2, faces geometric constraints that make observing objects near the sun either difficult or impossible during this period. This observational blackout is not merely a technical inconvenience. It is a critical window during which any potential course adjustments, maneuvering, or structural changes could occur undetected. The universe's silence during these weeks might hide signs of intentional behavior or subtle engineering that would otherwise be observable. When the sun's glare finally recedes and the object re-emerges into view, the subsequent data, its trajectory, brightness, spectral composition, will be scrutinized for anomalies, and the story of this interstellar visitor may finally be clarified. Until then, All we can do is prepare for what might come. The upcoming weeks will be a test, not just of our telescopic capabilities, but of our understanding of the universe's patterns. The forthcoming blackout period begins in late October 2025 and stretches into late November, spanning approximately 4 weeks. During this interval, the most active and intriguing interstellar object we have ever monitored will vanish from our direct view. The European Space Agency has officially confirmed this timeline, emphasizing that the object is expected to reappear in late November and carefully managing public expectations accordingly. Throughout this conjunction phase, observational opportunities will be exceedingly limited. While Mars Express and the Trace Gas Orbiter may attempt distant monitoring around October 3rd, it's important to recognize that these spacecraft are not optimized for such faint distant targets, and their signals will be weak, resulting in a poor signal-to-noise ratio. Now let's examine why this blackout window could be considered tactically advantageous, if and only if there is something artificial at work. Imagine for a moment that you are piloting a spacecraft through an alien star system. Your goal might be to study the inner planets, collect measurements, or deploy instruments and probes. But equally important is the need to avoid detection by any observers on those planets. What strategy would you employ? The answer is to synchronize your closest approach with a period when the dominant intelligent species, potentially us, are unable to observe you. You would use their star as a natural shield, conducting your maneuvers during what could be called their solar eclipse of awareness. Avi Loeb, a prominent astrophysicist, has repeatedly referred to this as the perfect time to maneuver. In numerous interviews and essays, he has highlighted that if a craft like 3IATLAS aimed to alter its course, fire thrusters, deploy secondary objects, or perform any other activity that might reveal its presence, the optimal moment would be during this conjunction window. By the time Earth-based observatories regain line of sight in late November, evidence of any such maneuvering would likely be obscured or diluted. The craft would have transitioned onto a new trajectory, but without continuous real-time tracking, astronomers would find it increasingly difficult to precisely determine when or how the change took place. Let me be clear. What I am describing here is pure speculation, a hypothetical scenario. There is no current evidence to suggest that 3IATLAS possesses maneuvering capabilities, nor that it plans to do anything during the conjunction beyond following its predicted orbit and outgassing naturally as it responds to solar heating. Nonetheless, the timing raises an intriguing question. Can we observe or detect any activity during this period? The short answer is barely and only indirectly at best. Instruments designed to study the sun's corona, known as coronagraphs, can occasionally detect bright comets passing very close to the sun's limb. The Solar and Heliospheric Observatory, SOHO, for instance, has identified thousands of sun-grazing comets through this method. However, 3IATLAS is not passing sufficiently close to the sun for these instruments to observe it. Its current position is too distant, and its faintness makes detection unlikely, rendering coronagraphs essentially a dead end for observing this object during conjunction. Another potential method is radio occultation, where signals from spacecraft are bent or scattered as they pass behind the sun. In theory, this could be used to detect an object's presence by observing perturbations in radio signals caused by the solar plasma and magnetic fields. But in the case of 3IATLAS, it is not a radio emitter, nor is it large enough to produce a detectable gravitational lensing effect. Consequently, radio occultation techniques are unlikely to yield any useful information about the object during this period. Radio occultation, the method where signals from spacecraft are bent or disturbed as they pass behind the sun, is unlikely to provide meaningful insights in this scenario. While there are some highly speculative monitoring techniques, such as cosmic ray detectors and meteoroid counters embedded in spacecraft scattered across the solar system, These instruments could, in theory, detect unusual particle fluxes if the comet were shedding material in unexpected or deliberate ways. However, these devices are not optimized for targeted comet observations. Their measurements tend to be noisy, and interpreting such data would be challenging at best. The stark reality is that during the period of solar conjunction, our observational capabilities are effectively null. We are, in essence, blind. What remains crucial and what underscores the importance of post-conjunction observations is preparation. Astronomers are meticulously planning to scrutinize 3IATLAS the moment it reemerges from behind the Sun, armed with a clear understanding of what signs to look for. Their checklist includes several key metrics. Firstly, they will examine the light curve for continuity. The question here is whether the brightness of the comet has evolved as expected based on established solar heating models. Sudden jumps or drops could suggest structural changes or the release of material, hinting at non-natural activity. Secondly, spectroscopy will play a vital role. Observers will assess whether the ratio of carbon dioxide to water remains at the remarkable 8:1 level, or if it has shifted, indicating possible chemical or thermal changes. The presence of iron emission lines appearing alongside nickel, something expected in natural thermal progression, would be another significant indicator. Thirdly, position residuals will be analyzed. This involves comparing the comet's observed position against predictions that assume a purely gravitational trajectory. Any deviations, small discrepancies, could suggest acceleration or other forces at play, potentially pointing to non-natural influences. Fourth, changes in the morphology of the tail or coma are scrutinized. New jets, asymmetries, or unexpected features that weren't present before the Sun's obscuration could be telltale signs of activity or engineering. Fifth, follow-up polarimetry measurements are planned. These will determine whether the extreme negative polarization phase observed earlier persists or has evolved, offering further clues about the surface or outgassing processes. All of these metrics are quantifiable and scientifically testable, and crucially, the data will be available within days of the comet's reappearance. Yet what keeps many astronomers, like Avi Lowe, and an increasing number of professionals awake at night is the knowledge that if any unusual activity occurs during the blackout, we may only learn about it afterward. We would see the evidence, but we would have missed the actual event itself. Much like arriving at a crime scene after the fact and trying to piece together what transpired from forensic clues alone. This lack of real-time observation adds a layer of uncertainty and raises the stakes for post-event analysis. The timing of these observations is further complicated by the close approach of the comet to Mars on October 3rd, 2025, just days from now. During this encounter, which will bring the object within roughly 30 million kilometers of the red planet, the European Space Agency plans to aim Mars Express and the Trace Gas Orbiter at it. Although these spacecraft are not specialized comet hunters and their viewing geometries are less than ideal, they will make an effort. Why does Mars matter in this context? Because it offers a different vantage point. Should the comet be engaging in directional activity, venting asymmetrically, emitting signals, or deploying secondary objects, observers on Mars might detect phenomena that Earth-based telescopes could miss. Multiple perspectives help reduce ambiguity and strengthen the analysis. Then, on March 16, 2026, the comet will pass within approximately 0.358 astronomical units of Jupiter, about 33 million miles. This proximity is sufficient to allow very detailed observations, assuming tracking remains reliable. Jupiter's immense size and its powerful magnetosphere make this encounter particularly significant, providing an excellent opportunity for long baseline triangulation and detailed characterization. If the spacecraft Juno remains operational, it could conduct an intercept, offering unprecedented in situ data. These multiple observation points, Earth, Mars, and Jupiter, form an intricate network of potential insights, each adding layers to our understanding of this enigmatic visitor. Jupiter's position in its orbit at that critical juncture will present an entirely different observational vantage point, a vantage point that could yield valuable insights. If NASA's Juno spacecraft successfully manages to execute a planned intercept, it would allow us to obtain in situ measurements directly from the object itself. This sequence of events, beginning with the flyby of Mars on October 3rd, followed by the period of solar conjunction and perihelion in late October through November, then the re-emergence of the object in late November and culminating with a close approach to Jupiter in March of 2026 is no accident. It's a carefully choreographed series of opportunities, a celestial dance of data collection points if we are attentive enough to recognize them. Now I want to address a concern that many might have, especially those pondering the implications of such an object. What if, during the time when our view is obstructed by the sun, something malicious or dangerous occurs? What if it releases something that could threaten Earth? It's a natural question given our innate fears and the unknowns involved. However, both NASA and the European Space Agency have been unequivocally clear on this point. They have firmly stated that the object designated as 3IATLAS poses no threat to our planet. The orbital geometry simply does not allow for an impact. Even if the object were to break apart into thousands of fragments during perihelion, those pieces would still not intersect with Earth's orbit. The closest approach distance predicted is approximately 1.8 astronomical units, more than 160 million miles away. To put that into perspective, the Moon, which orbits just about 240,000 miles from Earth, is vastly closer than this object's closest pass. Therefore, the risk of collision or impact is effectively non-existent. Could this object, in principle, release probes or smaller craft that might alter course and head toward Earth? Theoretically, yes, but the physics of such a maneuver would be formidable. Redirecting an interstellar object onto an Earth intercept trajectory would require an enormous change in velocity, on the order of kilometers per second. Achieving such a delta V would demand rocket-grade propulsion, something akin to firing a powerful engine in space. We also have the capability to detect the thermal signature of such an engine burn, even during the period of solar conjunction, provided the thrust were pointed toward us. Given our current technological acuity, such a burn would not go unnoticed. So what is the realistic worst-case scenario? It isn't one of active danger. Instead, it is one of ambiguity. It's the unsettling possibility that during the blackout period, when our observational tools are essentially blind, something unusual might happen. Perhaps an unanticipated course change, or an anomalous outgassing event, or the deployment of secondary objects that we cannot detect in real time. We would then be left to interpret the aftermath, trying to determine whether what we observe is merely natural outgassing or something more deliberate and engineered. The core issue is that solar conjunctions are not just inconvenient. They represent a significant gap in our continuous observational record. They are moments when we cannot rewind or rewatch what transpired. We can only interpolate what might have occurred, but we cannot see it directly. Loeb has consistently stressed this point in his writings and interviews. He refers to this period as the perfect window, not because he anticipates something specific will happen, but because if one were planning a mission with operational security in mind, this would be the optimal time to execute clandestine maneuvers. It's a window of opportunity, a fleeting moment where the universe's geometry shields activities from our direct line of sight, not proof of any intent, but a chance to act undetected. So what comes after this? In less than 4 weeks, 3IATLAS will pass behind the sun and fall silent, effectively vanishing from our view. We then wait, monitoring the limited signals we might still capture from Mars orbiters, preparing our instruments for the moment of reemergence. When late November arrives, we scrutinize the object's reappearance. If it appears exactly where predictions suggested it should be, exhibiting a light curve and spectral signatures consistent with natural cometary behavior, then the apparent coincidence likely explains the observations. In that case, the best explanation remains that we're dealing with an extraordinarily peculiar but ultimately natural interstellar comet. However, if the object's position at reemergence deviates significantly from predictions, or if its chemical composition shows unexplained shifts, or if new features, such as unexpected jets, structural anomalies, or anomalous emissions, manifest, then the situation becomes far more intriguing. Such surprises would deepen questions about its true nature and lend more credence to the hypothesis that we are not merely observing a natural object, but something else entirely, potentially artificial or engineered in origin. The impending silence of the sun's shadow is almost upon us, and once that silence is broken, our understanding of what lies beyond will inevitably deepen. While we may not uncover every detail, the knowledge gained will be significantly greater than before. This anticipation leads us to a provocative notion that has lingered on the fringes of our collective curiosity and skepticism throughout this entire discussion. What if the so-called 3IATLAS isn't merely a solitary object drifting through space? What if instead it functions as a kind of vessel, a carrier, designed to undertake interstellar journeys, possibly carrying within it smaller probes or devices that could be deployed once it reaches a suitable star system? Let's revisit this idea, what some might call the mothership hypothesis, a concept that has been explored in scientific circles, notably by Avi Loeb, in the context of interstellar objects. It's crucial to emphasize from the outset that what we're about to consider is pure speculation. This isn't established scientific fact, but rather a framework, an imaginative scaffold, meant to guide us in recognizing potential signs that an interstellar visitor might be more than just a natural, inert chunk of ice or rock. The core of this hypothesis is simple yet profound. Instead of assuming that interstellar objects are monolithic entities, single solid bodies, they might be complex engineered vessels. These vessels could be purpose-built crafts capable of traversing the vast, cold voids between stars, perhaps equipped with smaller deployable probes or instruments designed for reconnaissance, data collection, or perhaps even communication once they arrive at their destination. Think of it as a cosmic research vessel, launching survey drones or probes to scout the local environment of a star system, gathering valuable data before retreating or relaying information. This idea isn't new. Avi Loeb first introduced a version of it after the detection of Oumuamua, suggesting that it might have been a defunct light sail, an artifact of some advanced civilization, or that it could have carried smaller probes that we simply failed to detect. Although the scientific community was naturally skeptical, viewing it as a wild hypothesis, this proposition was not about Oumuamua itself, but about establishing a broad, conceptual framework. Essentially, it was an invitation to consider the possibility that some interstellar objects might be deliberate, engineered hardware rather than natural bodies. Now, with the arrival of 3IATLAS, those questions are resurfacing with renewed urgency. Not because we have definitive evidence, but because the object's peculiar behavior, its trajectory, chemistry, and physical features prompt us to ask, if it were a carrier, what signs might indicate as much? What observational clues should we be looking for if this object isn't just a random comet, but a purposeful vessel? One potential signature is the presence of brief, intense brightness spikes, so-called micro-brightness variations, that could occur if the object is releasing smaller secondary objects, probes, or instruments. These releases might cause short-lived localized illumination as the surfaces are exposed or materials vented into space. Such spikes would typically last only minutes or hours, a fleeting signature that could be missed without high cadence, continuous monitoring. Detecting such brief events would require observations specifically designed to catch rapid fluctuations. Using high-frequency photometry, specialized radar setups, or instruments capable of identifying specular reflections, which occur when smooth surfaces reflect signals coherently and strongly. In addition to brightness spikes, another telltale sign of a carrier might be the formation of debris trains following deployment. If, during the solar blackout, the object had indeed released probes, fragments, or secondary objects, these could manifest as a linear trail, an accumulation of smaller bodies trailing behind the main body. Such debris trains would be faint and diffuse in wide-field imaging but could be identified through careful analysis, especially if multiple observations are coordinated across different vantage points. While these signatures are speculative, they are scientifically plausible and, importantly, within the realm of detection with current technology. The key lies in targeted high-sensitivity observations at the right times, focusing on rapid brightness variations and the potential presence of debris structures, both during the moments when the primary object is visible and in the aftermath of its reemergence. In essence, the mothership hypothesis invites us to expand our thinking about what interstellar objects could be and what signals they might leave behind. It encourages us to look beyond the traditional view of a natural comet and consider the possibility of deliberate engineering, of vessels designed for exploration, reconnaissance, or communication, hidden within the mysterious travels of bodies like 3IATLAS. Natural comets are known to sometimes break apart, shedding debris in the process, which makes distinguishing between a natural fragmentation and a deliberate deployment quite challenging. This intricacy becomes especially relevant when evaluating claims like the headlights observation. Loeb's note of a luminous sunward glow could be interpreted, at least speculatively, as evidence of active thermal regulation rather than purely natural phenomena. If the object known as 3IATLAS were an artificial craft, perhaps a probe or a vessel, using the sun's thermal energy for power or cooling, then its sun-facing side would likely be noticeably hotter. In such a scenario, if this sunward face were actively venting carbon dioxide to manage its temperature, acting as a kind of radiative radiator, the emission would be both bright and directional, precisely matching the bright localized glow described by Loeb. This is where the peculiar ratio of carbon dioxide to water, measured at about 8:1, becomes particularly intriguing. Unlike water ice, which sublimates at relatively higher temperatures, carbon dioxide can sublime at much lower temperatures. If one were designing a passive thermal management system for a spacecraft approaching a star, the ideal volatile would be one that vents easily and efficiently, carries heat away without the need for active pumps or compressors. And carbon dioxide fits this role perfectly. Water, by contrast, is more cumbersome, stickier, more prone to freezing in inconvenient locations, and more difficult to manage thermally. Therefore, a craft venting carbon dioxide as a coolant would produce, from a chemical perspective, a signature that closely resembles what instruments like the James Webb Space Telescope, JWST, and SPHERICS have observed: a bright sunward emission lobing outward from the object. It's important to emphasize that this is pattern recognition, an intriguing correlation rather than definitive proof. This is a form of pattern matching, not a verification of artificiality. Moving on to the peculiar chemical signatures, the detection of pronounced nickel emission lines without a corresponding iron signature is among the most unusual aspects of 3IATLAS. Natural explanations for this phenomenon do exist. For instance, the presence of organometallic compounds or photon-stimulated desorption pathways that preferentially release nickel atoms. These mechanisms are exotic and not yet fully understood or fleshed out in scientific literature. One plausible hypothesis is that the nickel observed in the coma could be an effluent byproduct of internal processes. For example, if the object contained nickel-bearing compounds such as nickel tetracarbonyl, which are used industrially for their volatility, then chemical reactions inside the vessel, possibly driven by internal heat sources or reactions, might break these compounds down, releasing nickel atoms into the surrounding environment. Considering that nickel compounds like nickel tetracarbonyl are highly toxic and volatile, it's unlikely they would be materials intentionally used in spacecraft, especially by current human standards. Yet, if an advanced civilization had developed sophisticated engineering solutions, perhaps such compounds could be part of some thermal or chemical system. If internal energy sources or reactions were fragmenting nickel-containing materials, then it would be natural to observe nickel atoms being released into the coma. If the materials involved did not include similar amounts of iron, or if iron was stored or processed differently, then the spectral signature would show a dominance of nickel emissions with minimal iron presence. Once again, this is speculative but not outside the realm of physical possibility. Why might an interstellar probe choose to deploy secondary objects or disperse materials during the solar conjunction window? The reasoning hinges on operational security. During conjunction, ground-based tracking is minimized because the object is aligned behind the Sun from Earth's perspective, making it difficult to observe. If an entity wanted to deploy sensors, probes, or other secondary objects, either passively descending toward the planets or actively changing course, they would prefer to do so at this window, when the likelihood of detection by terrestrial telescopes was at its lowest. This timing would be strategic. Deploying during a period of observational silence would reduce the chances of detection or interception of any maneuver or deployment. It's a logical tactic if one wanted to maintain stealth while conducting complex operations within the solar system. However, it's essential to consider the counter-arguments. Many phenomena observed in comets can be explained through conventional natural processes. For example, dust jets and phase effects, optical illusions caused by localized active regions on the comet's nucleus, can produce bright directional features that resemble headlights. Comets are inherently irregular and asymmetric objects. Localized active regions can generate jets that point sunward, creating the appearance of bright, headlight-like emissions. In addition, the high carbon dioxide to water ratio, while unusual, is not impossible within the natural variability of comet chemistry. Some comets, such as Comet C-2016-R2, pan-stars, have shown unusually high levels of carbon monoxide and carbon dioxide, likely reflecting a formation environment in a particularly cold or chemically distinct region of their star-forming nebula. Such outliers, though rare, are documented and align with the understanding that comet compositions, the complex interactions among sunlight, dust particles scattering light, and the geometry of observation can create a multitude of optical illusions that may deceive even seasoned astronomers. Before jumping to conclusions about extraterrestrial technology, it is essential to first eliminate these mundane natural explanations. For instance, the existence of carbon dioxide-rich comets is well documented, and one notable example is Comet C-2016-R2, discovered in the year 2016. This particular comet became famous as an outlier due to its unusually high concentrations of carbon monoxide and carbon dioxide, likely because it originated from a notably colder region within its parent system. Such unusual chemistry is not impossible. Indeed, it occurs naturally, albeit infrequently. While rare, these phenomena remind us that nature can produce highly unusual yet entirely natural objects. Furthermore, the phenomenon of fragmenting comets is commonplace within our solar system. Should 3I/ATLAS undergo disintegration during perihelion, the point closest to the Sun, it would likely be due to the intense thermal stress and gravitational tidal forces acting upon it. Such fragmentation would generate debris which would appear as a swarm of ice and rocky fragments. It is crucial to recognize that this debris would not be an indication of artificial probes or extraterrestrial technology. Rather, it would be consistent with natural breakup processes. Distinguishing between natural fragmentation and deliberate deployment of objects, such as probes, using Earth-based observations alone is exceptionally challenging, if not impossible, without highly detailed tracking data. So what observable consequences would suggest the presence of artificial control if the carrier hypothesis holds true? The most compelling evidence would be the detection of anomalous accelerations after the object re-emerges from behind the Sun. If 3I/ATLAS returns on a trajectory that deviates from what gravitational models alone can explain, specifically if there are residual position discrepancies that cannot be accounted for by outgassing or radiation pressure, they could serve as a smoking gun indicating active propulsion or control systems. Such non-gravitational acceleration would strongly suggest the presence of thrust or maneuvering capability. Another potential indicator involves transient meteor entries. If small probes or fragments had been deployed from the object and some of these entered Earth's atmosphere, they might produce observable meteor events. However, caution must be exercised here to avoid sensationalism. Earth constantly experiences a barrage of natural meteoroids, tens of thousands of meteors each day, so a handful of unusual meteor reports during or immediately after the conjunction period would not, in isolation, prove anything extraordinary. To establish a credible connection, coordinated observations from multiple meteor camera networks would be required. These networks would need to perform precise trajectory reconstructions to determine if the meteors could be confidently linked back to 3I/ATLAS. While such coordination is possible, it demands discipline and meticulous analysis. Additionally, radar follow-up observations could provide critical insights. If astronomers manage to secure radar time on facilities like the Goldstone Solar System radar or successor systems to Arecibo, which has unfortunately collapsed, they could attempt to detect the object and look for unusual return signals, such as specular reflections or geometric shapes, that do not resemble a typical debris field. These signals could hint at artificial structures or controlled objects. What specific data is necessary to rigorously test the carrier hypothesis? High-cadence photometry during the object's re-emergence is paramount. Continuous brightness measurements taken at intervals of just a few minutes, rather than hours, are essential to catch transient events such as sudden outgassing or surface activity. Similarly, deploying wide-field monitoring systems like the All-Sky Meteor Orbit System, AMOS, can help detect any unusual meteoric activity associated with the object's passage. Precise astrometric measurements, ideally with an accuracy reaching milliarc seconds, should be obtained from advanced ground-based telescopes, the Gaia spacecraft, and if possible, the James Webb Space Telescope. Comparing these measurements to predicted positions based on gravitational models can reveal subtle deviations indicative of active maneuvers. However, it is crucial to recognize and openly acknowledge the risks involved in such investigations. The primary challenge lies in the fact that many of these signals can be subtle and easily confounded by natural phenomena or observational artifacts. There is always a danger of falling into confirmation bias, where we interpret ambiguous data as evidence of artificiality simply because it is unexplained or unusual. Rigorously pre-registering hypotheses and specific observational criteria is vital to avoid the pitfalls of post hoc rationalizations. Only through systematic, unbiased data collection and analysis can we confidently differentiate between natural outliers and potential signs of extraterrestrial technology. In essence, these observations and data collection efforts are designed to establish a clear, empirical foundation. Should the data reveal anomalies, such as unexpected accelerations, structural changes, or electromagnetic emissions, these would substantially bolster the case for artificial origin. Conversely, if the object behaves in accordance with known natural physics, then the simplest explanation remains that it is a highly unusual yet natural interstellar comet. The pursuit of such evidence is not just about identifying alien technology, but about expanding our understanding of the paradoxically, our human tendency to recognize patterns, agency, and purpose, even where none exist, is woven into the very fabric of our cognition. This phenomenon, known as pareidolia, causes us to see faces in clouds, discern faces in random arrangements of rocks or shadows, and interpret static noise as messages or signals. When our minds are primed to detect signs of extraterrestrial probes or advanced alien technology, this bias becomes even more pronounced. We're quick to find what we're seeking, even if what we interpret as evidence is nothing more than ordinary cosmic debris, like ice chunks drifting through space. Throughout the history of astronomy, misconceptions and false alarms have been commonplace, each fueled by our innate pattern recognition and expectations. For instance, Percival Lowell famously believed he saw canals on Mars, driven by his conviction that the planet's surface featured artificial waterways, a notion rooted in his desire to find evidence of intelligent life. Similarly, early SETI, search for extraterrestrial intelligence researchers, sometimes mistook terrestrial radio interference for alien signals, leading to needless excitement and false hopes. The legendary WOW signal, detected in Udna Tisicha Davidsat Sem Desat Sem, remains an enigmatic anomaly, unexplained and never repeated, serving as a cautionary reminder of how easily we can be fooled by our biases. To guard against these cognitive pitfalls, scientists advocate for pre-registration of hypotheses and predictions. This means explicitly defining in advance what observations or measurements would serve to confirm or disprove a particular theory, rather than retroactively fitting explanations to anomalies after the fact. Such an approach ensures objectivity, allowing the data to guide conclusions instead of our expectations or desires. The mothership hypothesis is a prime example of this scientific discipline. It's a testable idea, one that makes specific predictions about the behavior and signatures of an interstellar object if it were, in fact, a deliberately deployed probe or an artificial craft. If subsequent data, collected after a conjunction blackout period, align with these predictions, the hypothesis gains credence. If they do not, it must be discarded. However, herein lies the uncomfortable truth. If the data instead show features consistent with deployment or maneuvering, such as unexpected accelerations, structural anomalies, or emissions, then we enter uncharted territory. We would no longer be dealing with a simple natural comet, but with something that actively chose to arrive here, perhaps with intent. This raises a profound historical question. Has humanity ever used the sun's position to conceal or facilitate covert operations? While interstellar visitors have yet to do so, at least as far as we know, humans have certainly exploited the geometry of solar conjunctions for operational advantage. The tactical use of the sun's position in spaceflight history is well established and offers valuable insights. Part 7 of our discussion explores these behind-the-sun tactics in aerospace history. Solar conjunction isn't merely an astronomical curiosity. It's a practical operational tool. For space agencies and mission planners, this period when a spacecraft or celestial object passes behind the sun from Earth's perspective has often been used to advantage, or at least as an unavoidable obstacle to communication. Take Mars exploration as a classic example. Approximately every 26 months, Earth and Mars align in such a way that Mars appears to pass behind the Sun from our vantage point. During these windows, which last about 2 weeks, radio signals transmitted between Earth and Mars become heavily distorted or entirely blocked by the Sun's hot, turbulent corona, a swirling plasma of charged particles and magnetic fields. This interference disrupts real-time communication, rendering data transmission slow, unreliable, or impossible. To manage this challenge, NASA and the European Space Agency, ESA, have established protocols. During solar conjunctions, Mars rovers are typically put into safe mode, ceasing driving operations and performing only essential functions, while orbiters continue to collect data but store it on board without transmitting until normal communication resumes. This enforced silence is a strategic necessity. The geometry simply doesn't permit reliable contact. Once the conjunction concludes and the Sun's interference diminishes, operations can pick back up seamlessly. A similar problem existed during the Apollo lunar missions. When spacecraft passed behind the Moon, out of direct line of sight, mission control lost contact, creating temporary communication blackouts. During these periods, astronauts operated independently, and mission teams relied on pre-programmed commands and stored telemetry. For instance, during Apollo Vosum's critical translunar injection burn, the spacecraft was behind the Moon, and the crew had no real-time communication with Earth. The moment the craft re-emerged, mission control confirmed that the maneuver had succeeded, adding a layer of suspense to an already tense operation. Beyond NASA, military and intelligence agencies have long recognized and exploited the Sun's geometry for operational secrecy. Satellites in specific orbits may time maneuvers or data transmissions during periods of solar conjunction, when the Sun's glare acts as a natural shield, obscuring activities from ground-based observation or adversarial tracking. During these windows, assets can perform sensitive operations with a reduced risk of during the periods when the lunar far side passes between the spacecraft and Earth. The Apollo modules would lose all radio contact with mission control. This occurs because the Moon itself acts as a solid barrier, blocking the radio signals that enable communication with Earth. For those intervals, which could extend to half an hour or more, the astronauts aboard the spacecraft found themselves entirely cut off from outside assistance. Mission Control was unable to receive telemetry data, could not issue commands, and had no way of providing immediate help if something went wrong. It was a silence enforced by the geometry of the Moon, an enforced radio blackout that added an extra layer of tension to already delicate maneuvers. It was precisely during one of these far-side passes on Apollo Vosum that astronauts Frank Borman, Jim Lovell, and Bill Anders executed a critical engine burn. Their goal was to leave lunar orbit and begin the journey back home. Because of the communication blackout, Earth had no confirmation of whether the maneuver had succeeded until the spacecraft re-emerged from behind the Moon's horizon. The entire operation was shrouded in suspense, as mission teams could only wait and hope that everything proceeded as planned until radio contact was restored. This enforced silence, and the uncertainty it fostered, amplified the stakes of a tense and historic moment. Now shifting from the open historical perspective to the clandestine realm, let's examine the classified side of such operations, because this is where the discussion becomes particularly fascinating. Military and intelligence satellites are engineered with precise spatial awareness, an understanding of geometry that is vital to their operational security. If you are operating a reconnaissance satellite, your primary concern is controlling who can see you and when. Certain orbits, such as geostationary or geosynchronous ones, keep satellites fixed over specific regions of the Earth's surface, making those satellites predictable targets for ground-based observation and tracking. Adversaries with optical or radar tracking capabilities can monitor these assets if they are in predictable positions. However, strategic timing of maneuvers and deployments can significantly reduce the risk of detection. If a satellite's operators coordinate moves during periods when ground stations or adversary tracking systems lack line of sight, such as during local daytime when optical telescopes can't observe, or when a satellite passes over vast unmonitored ocean regions, they can effectively minimize their exposure. The sun itself becomes an additional shield. When a satellite is positioned close enough to the sun from Earth's perspective, the intense glare prevents optical telescopes from observing it directly. This use of solar conjunction as a cover isn't mere speculation. It's a fundamental principle of orbital mechanics and operational security, well understood by military strategists. Geometry in this context becomes both a weapon and a shield. By exploiting the positioning of celestial bodies and the relative angles of observation, operators can conceal maneuvers and deployments, reducing the chances of detection and interference. Does this imply that the object known as 3IATLAS is employing such tactics? Not necessarily, at least current evidence does not confirm it. But if control of the object were in the hands of an artificial intelligence or an intelligent entity capable of navigation, it would be a highly logical strategy. Deliberately executing maneuvers during solar conjunction would be operationally advantageous, allowing the object to change course or deploy secondary probes without immediate risk of detection from ground-based or space-based sensors on Earth. The feasibility of such concealment, however, is nuanced. Could an object truly hide its maneuvers during a solar conjunction? The answer is both yes and no. Any significant change in velocity, what engineers call a delta V burn, inevitably produces some thermal signature. Chemical rocket engines, for example, generate considerable heat and produce visible thruster plumes. If 3IATLAS performed a burn with traditional propulsion during conjunction, infrared sensors operating across the solar system, such as those aboard NASA's space telescopes, might detect the resulting thermal flash. Similarly, the Department of Defense's classified early warning satellites, designed to identify missile launches via infrared signatures, could potentially observe a large, hot thruster burn. These satellites are highly sensitive to sudden increases in infrared radiation and are specifically tuned to detect thermal anomalies associated with large propulsion events. If a significant maneuver occurred even during a period of darkness from Earth's perspective, the thermal signature might be detectable by these assets. That said, the scenario changes if the object employs a small, efficient, and cold propulsion system, such as a venting of inert gases like nitrogen or carbon dioxide through a low-thrust, high-efficiency thruster. Such a burn would produce minimal thermal signature, especially if executed in a direction away from Earth and other major observation points. In these cases, the maneuver could be subtle enough to remain hidden from both optical and infrared sensors, effectively cloaking activity during the conjunction window. In summary, while a large, traditional rocket burn during solar conjunction would likely leave detectable thermal traces, a carefully planned, low-thrust, minimal heat maneuver could be executed without leaving obvious signs. This strategic critical aspect of tracking interstellar objects like 3IATLAS lies in astrometry, the precise measurement of their positions in space. Even if direct observation becomes impossible during a solar conjunction blackout, astronomers can still compare the object's location before and after this period. If, upon re-emergence in late November, 3IATLAS is found to deviate from its predicted path, specifically if its position no longer aligns with the trajectory calculated solely based on gravitational influences, that would serve as concrete evidence of an unexpected acceleration or maneuver. This discrepancy would highlight that some force or action altered its course during the conjunction gap, yet pinpointing the exact moment of this maneuver would remain uncertain. We would know it occurred during the period when observations were impossible, but not precisely when. Despite this uncertainty in timing, the fact that the trajectory has shifted would be unmistakable. Could such a maneuver be entirely concealed? Not entirely. While the thermal signature, such as heat emissions from thrusters, might go unnoticed or be too subtle to detect during the blackout, the gravitational effects are unambiguous and unchangeable. Gravity, after all, is relentless and unforgiving. Any change in velocity or course leaves an unmistakable imprint in the object's ephemeris, the detailed table of its predicted positions based on known physics. Post-conjunction astrometry becomes the ultimate forensic tool in this context. When observations resume, the measured position of 3IATLAS will either correspond with the predictions, indicating no deviation, or it won't. If it doesn't, the divergence is irrefutable evidence that the object was actively maneuvering. There is simply no way to fake the gravitational fingerprint. The physics remains constant and transparent. This leads to a vital point. Even if a deliberate maneuver occurs during the period when direct observation is impossible, say during the solar conjunction, the subsequent data will reveal it. We may lack the video footage or direct visual confirmation, but the forensic evidence, the residuals in the orbital data, will be conclusive. In science, these kinds of forensic clues often suffice. They tell a story through the physics, independent of direct visual evidence. The tactic of hiding a maneuver behind the sun is well understood and has been employed before. It's a recognized operational strategy, not magic. It provides temporary operational secrecy, allowing a craft to adjust its course without immediate detection. But this secrecy has its limits. It does not grant immunity from detection after the fact. The chemistry and composition of the object, for instance, could serve as a more telling sign than its trajectory alone. If 3IATLAS is venting carbon dioxide as part of some thermal or propulsion system, that chemical signature would persist and be evident in spectroscopic data. Such venting cannot be fully concealed because the spectral lines, these specific signatures, are baked into the spectrum we observe. This brings us back to the core mystery. Why is this object releasing such copious amounts of CO2? Why is the ratio of vented carbon dioxide to water so strikingly high, at a ratio of 8:1? And what does that reveal about the true nature of 3IATLAS? Let's delve into the carbon dioxide data because this is where the boundary between natural and artificial explanations becomes most apparent. It's a crucial piece of the puzzle, revealing insights that challenge our understanding of cometary chemistry and possibly hint at something more engineered or deliberate. In August of 2025, the James Webb Space Telescope conducted a detailed spectroscopic analysis of 3IATLAS. Using its near-infrared spectrograph, or NIRSpec, and its mid-infrared instrument, or MIRI, JWST measured the emission signatures of gases surrounding the comet. These instruments operate in the infrared spectrum, a range where various molecules such as water vapor, carbon dioxide, and carbon monoxide emit characteristic vibrational lines. The data, released shortly after the observations, revealed something highly unusual. Most notably, JWST detected a remarkably strong emission line at 4.3 micrometers, corresponding to vibrational excitation of carbon dioxide molecules. This is a familiar signature. Cometary comas often contain CO2, but what stood out was not just its presence, but its abundance relative to water vapor. The measured ratio of carbon dioxide to water was approximately 8:1, with a margin of about 1. In other words, for every molecule of water vapor detected, there were 8 molecules of carbon dioxide. This ratio is extraordinary and defies the typical composition of most known comets, where water usually dominates as the primary volatile. In a typical comet, water vapor outnumbers CO2 by a factor ranging from 10 to a few hundred, depending on the object. An 8-to-1 ratio indicates that this object is venting an unprecedented amount of carbon dioxide relative to water, almost as if the comet were primarily composed of CO2, or perhaps actively releasing it in a process that is far from standard sublimation. This unusual abundance raises fundamental questions about the formation and evolution of this comet. Is releasing 8 times more carbon dioxide than water vapor, and that's quite unusual. Normally, water ice is the most abundant and dominant frozen substance in comets. Think of comets as dirty snowballs, where the snow is primarily made of water ice. Other gases like carbon monoxide, carbon dioxide, methane, and ammonia do exist in comets, but they're usually only present in small amounts or as secondary components mixed in with the water ice. So discovering a comet where carbon dioxide is the main outgassed substance is akin to finding a snowman made entirely of dry ice. Possible, but highly uncommon. To put this into perspective, most comets have a ratio of carbon dioxide to water well below 1. Typically, for every 1 molecule of carbon dioxide, there are about 10 molecules of water, which gives a ratio of around 0.8. Having a ratio closer to 1/2, 0.8, is already considered high, and ratios of 2 or 3 are considered quite rare. But a ratio of 8, meaning 8 times more carbon dioxide than water, is practically off the charts, an extraordinary anomaly in comet chemistry. Further emphasizing how extraordinary this is, a space telescope called SPHEREX, designed to scan the sky in infrared wavelengths, also observed Comet 3IATLAS and reported something equally remarkable. It found that the bubble or cloud of carbon dioxide surrounding the comet's nucleus extends at least 348,000 kilometers away. To visualize this, the distance from Earth to the Moon is about 384,000 kilometers. So this comet is enveloped in a vast bubble of carbon dioxide almost as wide as the space between Earth and its satellite, the Moon. What's even more striking is that SPHEREX did not detect similar levels of water or carbon monoxide emissions from the same comet at that time. This suggests that the dominance of carbon dioxide isn't just a fluke or an anomaly of a single instrument measurement. It's a consistent feature of this comet's behavior. Now, what could possibly explain such an unusual composition? Scientists generally start with natural explanations, possible scenarios that could occur without invoking artificial or extraterrestrial causes. The first hypothesis concerns the comet's formation location. Comets originate in the cold outer regions of star systems, where the temperature is low enough for various gases to freeze into ice. Different molecules have different freezing points. For example, water ice condenses at temperatures between about 150 and 200 Kelvin, while carbon dioxide condenses at even lower temperatures, around 60 to 80 Kelvin. If Comet 3IATLAS formed in a particularly frigid part of its parent star system, perhaps far away from the star itself, maybe in a dense molecular cloud, it could have accumulated more carbon dioxide relative to water. This is entirely plausible because we know that different regions within the disks of material surrounding young stars have distinct chemical compositions. In our own solar system, the snow line, the distance from the sun where water ice becomes stable, is roughly at about 2.7 astronomical units. Beyond that, where it's colder, other ices like carbon dioxide, methane, and ammonia freeze. A comet forming beyond the carbon dioxide snow line would naturally be richer in carbon dioxide than in water. The second natural explanation involves radiation processing. Space is not empty. It's filled with cosmic rays, ultraviolet light from stars, and high-energy particles that bombard objects over millions of years. These energetic interactions can chemically alter the surfaces of comets, breaking apart water molecules and creating a crust that has been radiation processed. If the surface layers of Comet 3I-ATLAS had been depleted in water due to this process but still retained significant amounts of carbon dioxide, then early outgassing from the comet would show a high ratio of carbon dioxide to water. As the comet travels closer to the sun and heats up, this crust could erode or sublimates away, exposing fresher, more typical ice beneath. This natural process could explain why the comet's initial outgassing appears so unusual. In essence, these hypotheses suggest that the comet's strange chemistry could be the result of where and how it formed, or how it has been altered over the eons by space radiation. Both entirely natural scenarios consistent with what we understand about comet formation and space chemistry. If this were an artificial construct, say, a spacecraft or probe, then venting carbon dioxide as a cooling mechanism would be both practical and logical. In the vacuum of space, traditional methods of heat dissipation like conduction or convection are impossible, since there's no atmosphere or medium to carry away thermal energy. Instead, spacecraft rely heavily on radiative cooling or the venting of fluids that absorb and carry away heat. Carbon dioxide, with its favorable properties, would serve exceptionally well in this role. It is chemically stable, non-corrosive, and sublimates at temperatures that are easy to manage, making it an ideal working fluid for thermal regulation. Its thermodynamic characteristics are well understood, and in fact, on Earth, carbon dioxide is already employed in some refrigeration systems precisely because of these qualities. If an interstellar probe or craft were harnessing solar energy, perhaps through thermal radioisotope generators, photovoltaic panels, or other advanced power systems, then it would inevitably produce waste heat. To prevent overheating and maintain operational stability, venting carbon dioxide could serve as an efficient passive cooling strategy. As the craft approaches the sun, increasing thermal input would lead to more venting of CO2, effectively radiating excess heat away into space. This process would be a straightforward thermal management solution, leveraging the properties of carbon dioxide to regulate internal temperatures without requiring complex active cooling systems. In this context, the observed abundance of carbon dioxide, especially with an unusually high ratio compared to water, could be a signature of such engineering. It aligns with what we know about thermodynamics and spacecraft design, providing a plausible explanation for why an artificial object might preferentially vent CO2, particularly if it is designed to optimize heat dissipation while minimizing complexity. This hypothesis, while speculative, fits within the realm of known physics and engineering principles, and offers a compelling narrative for the chemical peculiarities observed in the comet's coma. As a spacecraft ventures closer to the sun, it faces an escalating challenge. Shedding the accumulating heat effectively becomes critical. This necessity naturally leads to venting more of the coolant, most notably carbon dioxide, since it sublimates at manageable temperatures and efficiently carries heat away. Unlike water, which presents a host of complications, CO2 offers a pragmatic solution. It remains gaseous at lower temperatures, is non-corrosive, lightweight, and easier to manage in the vacuum of space. Water, on the other hand, is a troublesome choice for thermal regulation because it freezes at inconvenient temperatures, is corrosive, and adds unnecessary mass. For these reasons, an engineering perspective suggests that an artificial vessel designed with thermal efficiency in mind would logically favor an Vossum-Tominus-Odin ratio of carbon dioxide to water, aligning with the properties of a well-optimized cooling system. Such a ratio is not just plausible, it's consistent with practical spacecraft design. However, here's the crucial point. This same ratio, along with the associated chemistry, can also be found in natural comets, especially those with unusual formation histories. A high carbon dioxide to water ratio does not unequivocally indicate artificial origin because certain natural processes can produce similar chemical signatures. Therefore, chemistry alone cannot serve as the definitive criterion to distinguish between a natural object and an engineered one. To make that distinction, scientists must look at how the object's properties evolve over time, their temporal evolution. If 3I/ATLAS is a natural comet, its volatile composition should change predictably as it interacts with the sun's heat. As it approaches perihelion, surface layers, initially rich in volatile compounds, should gradually erode or sublimate, revealing deeper layers with different compositions. Specifically, water ice, which sublimates more readily at higher temperatures, would begin to dominate the outgassing. This process should cause the initial high ratio of CO2 to water, say 8:1, to decrease progressively, perhaps halving to 4:1, then further to 2:1, and eventually reversing to a water-dominant composition. Such a clear, predictable pattern would strongly support the natural origin hypothesis. Conversely, if the object is artificial, the ratio may remain relatively stable over time, because it would be governed by engineered requirements rather than natural thermodynamic processes. An artificial spacecraft might regulate its heat dissipation based on onboard power systems rather than external solar heating, maintaining a steady ratio of vented gases. The key prediction here is that the carbon dioxide to water ratio should not show significant variation during the approach and perihelion phases. Monitoring these changes, particularly during and after perihelion, becomes a vital test. A natural comet should exhibit a predictable decrease in CO2 relative to water, whereas a stable ratio would hint at deliberate, engineered control. What can amateur astronomers do to contribute to this investigation? Surprisingly, quite a lot. Using narrowband imaging filters tuned to specific emission lines, such as the C2 SWAN bands or the hydroxyl OH line, amateurs can track the composition of the comet's coma over time. Coordinated efforts, where hobbyists around the world capture images in regular intervals, every few hours, can generate a high-resolution temporal data set that surpasses the limited scheduling of professional observatories. Citizen science thus plays a crucial role. Backyard telescopes equipped with decent cameras allow enthusiasts to contribute valuable data. Sharing these observations with organizations like the Minor Planet Center and the Global Comet Observation Community helps build a more comprehensive statistical picture, improving our ability to detect subtle changes in composition. Now, shifting focus from chemistry to the broader orbital context, the significance of the carbon dioxide anomaly becomes even clearer when we consider the trajectory of 3I/ATLAS within the solar system. The path it follows, including its sequence of planetary encounters, hints at a carefully orchestrated plan, whether naturally arising or deliberately engineered. When analyzing the orbital mechanics involved, a concept known as orbital chess, or gravitational assist, comes into play. A gravity assist, often called a slingshot maneuver, involves spacecraft using the gravity of a planet to alter its velocity and trajectory without expending additional fuel. This technique has been employed by missions like Voyager and New Horizons to reach the outer reaches of the solar system efficiently. The essence of a gravity assist is precision. The spacecraft must arrive at the planet at exactly the right place, at precisely the right time, with the correct velocity, to harness the planet's gravitational energy effectively. Any deviation from these parameters results in a failed assist, or worse, an unintended trajectory. It's akin to an intricate game of orbital chess, every move planned well in advance with the outcome heavily dependent on exact timing and positioning. In the case of 3I/ATLAS, the sequence of its close approaches, near Mars, perihelion near the Sun, then a near pass by Jupiter, mirrors a meticulously designed reconnaissance route. Whether this route was determined by natural processes or by deliberate planning remains a critical question. The details of the trajectory combined with its timing relative to planetary positions. Every maneuver and trajectory adjustment is meticulously planned years, sometimes thousands of kilometers ahead of time. In the case of 3IATLAS, it's not executing a gravity assist in the traditional sense, meaning it's not getting captured or accelerated by the gravitational pull of a planet, but its path does weave a precise sequence of close encounters that, if we were designing a reconnaissance mission, would serve as a textbook example of strategic flybys. Let's examine this itinerary in detail. On October the 3rd in the year 2025, 3IATLAS will pass within approximately 30 million kilometers of Mars. While this distance is far too great for a significant gravitational slingshot, meaning it won't substantially alter the comet's velocity or trajectory, it's close enough to be more than just a casual flyby. The European Space Agency has officially confirmed that their Mars Express orbiter and the Trace Gas orbiter will attempt to observe this event. But why does Mars matter so much from a scientific and strategic perspective? The answer lies in the vantage point. From this position, the orbiters can utilize their spectrometers, cameras, and other scientific instruments to examine the comet's coma and tail from angles that terrestrial telescopes simply cannot match. The geometry of this encounter is particularly advantageous for studying the anti-solar tail, the part of the comet's tail that extends away from the Sun, and the structure of the coma itself. These are precisely the regions where claims about headlights or unusual brightness, what Avilo refers to as the headlights phenomenon, are most relevant. Of course, the mission planners at ESA have been cautious. They acknowledge that Mars Express and TGO were not primarily designed for comet observation. Their main functions are focused on Mars' atmosphere, surface, and subsurface properties. Pointing these spacecraft at a distant, fast-moving comet is a secondary science opportunity. An intriguing one, but not a core mission goal. As a result, the expected signal-to-noise ratio in the data will be marginal, and the spatial resolution likely limited. Nevertheless, even limited data can be valuable. Should the comet vent asymmetrically or exhibit unusual brightness patterns, the Mars orbiters could potentially detect these phenomena. From a more speculative reconnaissance standpoint, Mars presents a compelling target because it's a planet with a dynamic atmosphere and surface features that change over time. This makes it an ideal candidate for sustained monitoring rather than just a brief flyby. The October 3rd encounter, therefore, offers a rare window to gather this kind of close-up, continuous data. Moving forward to late October 2025, the comet reaches perihelion, the closest point to the Sun, at about 0.96 astronomical units. For context, that's slightly less than the average distance from Earth to the Sun. This is the moment of maximum solar heating, which for a natural comet would trigger peak outgassing activity as volatile materials sublimated from the nucleus. For an artificial object, especially one hypothesized to harness solar thermal energy, this represents maximum power availability. It's the point where the object could potentially be most active in venting gases or adjusting its course. Simultaneously, this period marks the beginning of solar conjunction, the time when the comet will pass behind the Sun from Earth's viewpoint. During this phase, the observation window from our planet effectively closes, creating a significant gap in data collection. We've previously discussed how this timing is no coincidence. The geometry of the solar system aligns such that the comet's most active phase coincides with the period of least observability from Earth. This is a natural consequence of the positioning, but it's also a critical factor to consider when evaluating the behavior of the object during this period. Fast forward to March the 16th, 2026, when 3IATLAS will pass within approximately 0.358 astronomical units of Jupiter, roughly 33 million miles. To put this in perspective, Jupiter's innermost moon, Io, orbits at about 0.0028 astronomical units. This means the comet is not plunging into the Jovian system but is approaching it at a distance that allows for very detailed and high-quality observations. Jupiter, in addition to being the largest planet, is a magnetospheric powerhouse. Its magnetic field is the strongest in the entire solar system, extending millions of kilometers into space and creating a vast, charged environment. An object passing through this magnetic domain, be it natural or artificial, would interact with the magnetosphere in potentially observable ways. Dust grains might become charged, plasma tails could form, and electromagnetic signals might be detectable. This flyby, therefore, represents an extraordinary opportunity to gather a multifaceted data set, combining optical, infrared, and electromagnetic observations from several vantage points. In essence, the trajectory of 3IATLAS appears deliberately designed, or coincidentally aligned, to enable these strategic encounters with Mars early in October, the Sun at perihelion late in October, and Jupiter in mid-March. Each offers a different environment and a unique opportunity to observe and analyze the object. The magnetosphere surrounding a planet like Jupiter is teeming with charged particles, plasma, and intense radiation. When an object traverses this environment, it doesn't go unnoticed. It interacts with these energetic fields and particles. Dust grains on the object's surface can acquire a charge, and as the object moves through the plasma, distinctive plasma tails may form, akin to the glowing trails seen behind comets. Furthermore, if the object possesses any conductive properties, be it metal, ionized gas, or other materials, Jupiter's formidable magnetic field will exert a significant influence on its behavior and structure. From a scientific perspective, the upcoming Jupiter flyby in March of 2026 presents an exceptional opportunity for long-range triangulation. Should the spacecraft Juno still be operational and capable of observing the comet, and if multiple ground-based telescopes around the world are actively tracking it, and if the James Webb Space Telescope can secure observation time, then we would have access to a multitude of vantage points, spread across hundreds of millions of kilometers in space. Such a configuration allows for stereoscopic three-dimensional observations on a scale spanning the entire solar system. From this, scientists could reconstruct the detailed three-dimensional shape of the comet's coma, analyze the gradients in its chemical composition, monitor plasma interactions in real time, and gather a wealth of data about its physical and chemical properties. In the realm of speculative reconnaissance, where curiosity about potential artificial origins runs high, Jupiter becomes the crown jewel of planetary flybys. If one were investigating the possibility of an engineered object, this sequence of planetary encounters provides three prime opportunities for data collection: Mars, the Sun, and Jupiter. Each environment presents its own unique conditions and potential insights. Whether for scientific curiosity or for probing the hypothesis of artificiality, these encounters serve as deliberate or incidental stations along a potential observational route. Now it's important to temper some of the excitement with a reality check regarding the concept of gravity assists. This is a common point of misunderstanding. Genuine gravity assist maneuvers demand highly precise delta-V adjustments, meaning the spacecraft must approach a planet at an exact angle and velocity, swing around it, and leave on a different trajectory with a carefully altered speed. The core principle is that the spacecraft effectively steals a tiny fraction of the planet's orbital energy, gaining velocity in the process. For this to occur meaningfully, the spacecraft must be captured within the planet's gravitational well, coming very close within a few planetary radii. In the case of the object in question known as 3I-ATLAS, that is not happening. Its closest approach to Mars is approximately 30 million kilometers away, roughly 80 times the distance from Earth to the Moon, rendering the planet's gravitational influence essentially negligible at that distance. Similarly, the planned flyby of Jupiter at about 0.358 astronomical units, roughly 33 million miles, while closer in astronomical terms remains outside the orbit of the Galilean moons. Jupiter's gravity will exert a slight perturbation on the object's trajectory, but it will not produce a meaningful or intentional gravity assist in the mission design sense. Instead, the object is simply following a heliocentric orbit dictated by its initial velocity and the Sun's gravitational pull. These planetary encounters, then, are incidental, geometric coincidences resulting from where the planets happen to be when the comet passes through their orbital paths. If someone were deliberately designing a reconnaissance mission, they wouldn't necessarily rely on gravity assists. Instead, they would chart a trajectory that intentionally brought the object into close proximity with points of interest: Mars, the Sun during perihelion, and Jupiter, precisely to maximize observational opportunities. Currently, the publicly available ephemerides, that is, the predicted positions published by NASA's Jet Propulsion Laboratory and the Minor Planet Center, align perfectly with a trajectory governed solely by gravity. No confirmed non-gravitational forces are influencing the object's path so far. Currently, the available astrometric data indicates no confirmed non-gravitational acceleration affecting the object so far. In other words, based on the measurements taken before the period of solar conjunction, it appears to be following a purely ballistic, gravity-driven path through space. However, these measurements were obtained prior to the blackout, and if any course correction, such as a thrust maneuver, a deliberate burn, or an active deployment, occurred during the period when the object is hidden behind the Sun, we simply will not know until it re-emerges on the other side. By then, the trajectory predictions, which rely on continuous data, will have diverged from reality, making it challenging to detect any deviations or anomalies that might suggest artificial control. So what observational patterns should scientists and astronomers focus on after the object reappears to test whether its trajectory was intentionally designed or manipulated? One key indicator is changes in the phase curve. The phase curve represents how the brightness of an object varies depending on the angle between the Sun, the object, and the observer. This angle is known as the phase angle. For natural comets, the phase curve is primarily influenced by dust scattering and gas emission, and it exhibits certain predictable features. If upon re-emergence the phase curve displays unexpected anomalies, such as sudden spikes, asymmetrical patterns, or deviations from standard cometary models, these could be signs of structural complexity or active surface processes that are inconsistent with natural behavior. Another critical pattern to examine is timing residuals. Essentially, this involves comparing the object's actual arrival times at predicted positions against the expected times based on earlier orbital calculations. If the object arrives noticeably earlier or later than predicted, beyond the margin of observational uncertainty, that signals the presence of unaccounted-for acceleration. Even minute, sustained thrusts acting over weeks can produce detectable shifts in timing, revealing possible external control or propulsion. High-resolution imaging of the object's rotation and morphology can also offer valuable clues. If follow-up observations show that its spin axis has reoriented or its rotation period has changed, either speeding up or slowing down, these variations could suggest internal mass redistribution or external forces acting upon it. While such rotational changes can occur naturally due to outgassing jets or surface activity, when combined with other anomalies, they become significant indicators of potential artificial influence. Importantly, None of these measurement techniques require exotic or unprecedented technology. All can be performed with existing telescopes, spectrometers, and imaging instruments. The main challenges lie in securing sufficient observing time, coordinating efforts across different observatories, and analyzing the data meticulously. If the object's trajectory was deliberately planned, if someone or something engineered its path, the encounters with Mars in early October and Jupiter in mid-March are likely to be more than mere coincidence. These planetary flybys could serve as strategically chosen waypoints or checkpoints in a reconnaissance tour. For instance, studying Mars during early October would provide a vantage point to observe potential outgassing or emissions from a different angle. Using the Sun's thermal energy during perihelion in late October could serve a purpose, perhaps for thermal management or energy harvesting, while the Jupiter encounter in March would offer a second distinct perspective, especially given Jupiter's powerful magnetosphere and the potential for electromagnetic interactions. In contrast, if the trajectory is purely natural, then these planetary intersections are simply coincidental, random points where an interstellar object's path crosses planetary orbits. Distinguishing between these scenarios hinges on careful observation, monitoring whether the object behaves precisely as gravitational physics predicts, with no signs of additional forces or variations. Consistency with natural models, such as predictable outgassing patterns, stable chemical composition, and expected orbital mechanics, would favor the natural explanation. Conversely, deviations from expected behavior, such as unexplained accelerations, structural transformations, or electromagnetic anomalies, would lend credence to the idea that the trajectory was engineered. Such anomalies, especially if they occurred during or after the planetary encounters, could be interpreted as signs of a designed path, possibly implying the presence of artificial control systems. This leads to a broader consideration: the possibility of an engineered or purposeful trajectory. The pattern of encounters, timing, and unusual chemical signatures might not be coincidental. They could reflect an intentional design, an engineered itinerary that maximizes observational opportunities while minimizing detection chances, especially during periods when the object is hidden behind the Sun. Ultimately, the key lies in patience and rigorous measurement. Observations following the reemergence, comparing predicted and actual positions, analyzing spectral signatures, and scrutinizing the object's morphological and rotational characteristics are the tools that can help us discern whether we're witnessing a naturally occurring interstellar visitor or something more, an engineered probe, perhaps even a craft from an advanced civilization. Part 10 of the Juno discussion introduces a provocative and highly strategic proposal: the idea of repurposing NASA's Juno spacecraft for an intercept mission to the interstellar comet known as 3IATLAS. This concept, detailed in a peer-reviewed publication dated September 20th, 2025, appeared in the esteemed journal Aerospace and bears a title that directly challenges conventional expectations. It suggests that Juno could be redirected from its current scientific objectives at Jupiter to undertake a daring flyby of this mysterious visitor. The lead author of this paper is a researcher specializing in trajectory dynamics, and their meticulous analysis underscores that such an operation is not mere science fiction. Rather, it's grounded in the rigid laws of orbital mechanics. The feasibility is slim but real, hinging on precise calculations and innovative use of the spacecraft's existing capabilities. To understand the gravity of this proposal, it's essential to grasp Juno's current mission profile. Since its arrival at Jupiter on July 4, 2016, Juno has been orbiting the gas giant in a highly elliptical path, repeatedly swooping close to the planet's cloud tops to gather data about its atmosphere, magnetic environment, and interior structure. Over the years, the mission has been extended multiple times, and as of 2025, Juno remains operational, continuously returning valuable scientific insights. What makes this proposal bold is that Juno's main propulsion system, a powerful engine, has not been activated since its initial insertion burn in 2016. For nearly 9 years, it has been essentially dormant, yet, in theory, the engine's functionality remains intact, and some propellant may still be available. The plan hinges on executing a two-burn maneuver that exploits Jupiter's immense gravitational field as a gravitational slingshot, amplifying the effect of a relatively modest engine burn. This technique, known as a Jupiter-Oberth maneuver, named after Hermann Oberth, a pioneer of rocket science, relies on the principle that when a spacecraft is deep within a planetary gravity well, a small engine burn can produce an outsized change in trajectory. The gravity itself acts as an energy reservoir, allowing the spacecraft to catapult onto a new, more ambitious course with minimal fuel expenditure. The proposed timeline is specific and calculated. On September the 9th, 2025, Juno would perform a close perihelion pass near Jupiter, then execute a critical engine burn, requiring a delta V of approximately 2.68 kilometers per second, an amount comparable to the engine used in Apollo lunar landings. This significant propulsion effort would propel Juno onto a hyperbolic escape trajectory, effectively turning it into a fast-moving interceptor headed toward the inner solar system. Then, on March the 14th, 2026, Juno's new course would bring it into a high-velocity flyby of 3IATLAS at a relative speed of roughly 19 kilometers per second. That speed, while too rapid for traditional orbital rendezvous or capture, is perfect for a high-speed pass, allowing instruments on board to gather detailed, close-up data. During this flyby, Juno would pass within a few thousand kilometers of the comet's nucleus, a distance close enough that its suite of scientific instruments could analyze the comet's properties in unprecedented detail. Of particular interest are Juno's infrared and ultraviolet sensors. The Jovian Infrared Auroral Mapper, originally designed to study Jupiter's auroras, could measure the temperature and composition of the comet's coma, the cloud of gas and dust surrounding its nucleus. Meanwhile, the ultraviolet spectrograph would map the ultraviolet emissions from the coma, revealing the distribution of key gases such as carbon monoxide, water vapor, and hydroxyl radicals, providing insights into the comet's outgassing behavior and chemical makeup. This bold proposal exemplifies a combination of ingenuity and audacity. It leverages existing spacecraft hardware and fundamental physics to potentially provide the first direct close-up observations of an interstellar object in transit, an unprecedented scientific opportunity, and underscores the strategic thinking that space agencies are capable of when confronting the unknown. Juno, the spacecraft equipped with the Jovian Infrared Auroral Mapper, or JIRAM, stands ready with an array of sophisticated instruments designed for high-precision imaging and analysis. JIRAM, optimized specifically for infrared imaging, could meticulously map the thermal architecture of both the comet's nucleus and its surrounding coma, providing invaluable insights into the heat distribution and structural composition of this mysterious visitor. Complementing this, the magnetometer, known as MAG, offers critical capabilities despite comets not possessing intrinsic magnetic fields. Instead, they interact with the solar wind, creating a transient-induced magnetosphere. MAG could detect these interactions in real time, revealing whether the object exhibits any unusual magnetic properties that might hint at artificial origins or exotic compositions. The radio and plasma wave instrument, called WAVES, adds another layer of investigative power. It's capable of sensing plasma oscillations, radio emissions, and electromagnetic activity in the vicinity of the comet. Should the object be emitting any form of electromagnetic signals, whether natural phenomena or something more extraordinary, Waves would be the instrument to catch those signals, providing crucial data on its electromagnetic footprint. Meanwhile, the Juno CAM, a visible light camera not officially classified as a scientific instrument but included primarily for public outreach, offers the potential for stunning high-resolution imagery. It could capture detailed photographs of the nucleus and coma, revealing surface features, outgassing jets, or other structures that might inform hypotheses about its nature. Despite this impressive suite of instruments, the challenge lies not in the capabilities but in the risks associated with deploying Juno for such an encounter. Notably, Juno's main engine has remained dormant for nearly 9 years. Spacecraft engines are notoriously finicky. Propellant can settle, valves can stick, seals can degrade over time. There's a non-negligible chance that when commanded to fire, the engine might not respond as expected. It could fire partially, irregularly, or not at all, potentially leaving the spacecraft on an uncontrolled trajectory. If the engine were to fail during a critical maneuver, Juno could be lost, without enough propellant left to recover or stabilize its position, effectively sacrificing this flagship mission, which continues to deliver groundbreaking science at Jupiter. The authors of the recent paper have reached out to the Juno mission team for information regarding propellant margins and engine health, receiving a cautious response. The team acknowledged that although propellant reserves are available, executing a major retargeting burn would require a formal mission review, comprehensive risk assessment, and approval from NASA headquarters. Currently, there is no official plan to undertake such a maneuver. This situation, however, has entered the realm of political inquiry. On an unspecified date in 2025, sometime after the paper's publication, Congressional Representative Ana Paulina Luna, representing Florida, sent a letter to NASA urging the agency to evaluate the feasibility of redirecting Juno for an intercept of 3IATLAS. The letter emphasized the scientific significance of in situ measurements, underscoring the exceptional opportunity presented by the timing and geometry of the encounter. Such congressional interest is not merely symbolic. It can influence funding priorities, accelerate reviews, and push projects from the realm of possibility toward reality. At present, NASA has not publicly committed to retargeting Juno, nor have they announced a specific mission plan for such an endeavor. Yet the existence of a peer-reviewed trajectory study and active questions from Congress suggest this isn't merely a theoretical exercise. It represents a tangible, if still improbable, possibility. Should it materialize, the scientific payoff would be extraordinary. Humanity would have its first direct in situ encounter with an interstellar object, opening a new chapter in space exploration and interstellar science. The insights gleaned from such a mission could redefine our understanding of these visitors, whether they are natural objects or, intriguingly, artifacts of advanced civilizations. The story of interstellar visitors to our solar system is a compelling one, marked by missed opportunities and tantalizing possibilities. The first interstellar object, Oumuamua, arrived unexpectedly and departed before we could even organize a dedicated mission to study it. Its fleeting presence left us with only remote observations and limited data. Then came Borisov, which was observed from afar, allowing us to gather some details, but still without the chance for a close-up encounter. Now, with the arrival of the third interstellar visitor designated as 3IATLAS, a new chapter unfolds. This object stands out because we have accumulated enough warning, enough lead time, to potentially launch a deliberate intercept or to retarget a spacecraft already en route. This is a significant departure from the previous cases. It represents the first time we might actively engage with an interstellar body before it leaves our vicinity. An intercept mission with 3IATLAS could yield invaluable insights, providing direct measurements of its shape, potentially comparable in size to a small asteroid, and its composition, which would clarify many uncertainties. Such a mission would also be instrumental in resolving whether the curious headlights, bright directional emissions observed earlier, are genuine features of the object or merely artifacts of observational geometry. It would allow us to map the magnetic and plasma environment surrounding the object, revealing how it interacts with the solar wind and magnetic fields. Moreover, detecting any electromagnetic emissions, whether natural or engineered, would be a game changer. Most critically, a close flyby would produce imagery at resolutions far beyond what telescopes can achieve from Earth or orbit, offering a detailed look at the object's surface features, structure, and possible anomalies. If 3IATLAS is artificial, a probe or craft rather than a natural object, a flyby with NASA's Juno spacecraft could potentially uncover unmistakable signs of technology. Observations might reveal structures, geometric features, or anomalies that defy natural explanations. Data could include unusual surface features, signs of deliberate deployment, or other indicators that point to an engineered origin. Any anomalies detected would be difficult to dismiss, fundamentally challenging our understanding of the cosmos and our place within it. Conversely, if 3IATLAS is a natural interstellar comet, a Juno flyby would still be profoundly transformative. It would expand our knowledge of interstellar cometary composition, providing clues about the materials and conditions in other star systems. We would gain insights into outgassing mechanisms, the physics governing objects that have spent eons drifting in the dark, cold regions between stars, and the processes that shape such objects during their journey through space. However, engaging in such an intercept involves a serious risk calculation. Juno is not a small investment. It is a mission that has cost billions of dollars over its operational lifetime. It is currently a functioning spacecraft, orbiting and studying Jupiter, with a well-established mission profile. Diverting Juno for a risky one-time intercept with a possibly ambiguous target raises questions about resource allocation, scientific priorities, and mission integrity. NASA's decision-making process is complex and layered, what's known as Byzantine, involving mission scientists, program managers, leadership at NASA headquarters, budget analysts, and political stakeholders. The involvement of Congress suggests political interest and support, but interest alone does not guarantee action. To determine whether such an intercept is truly underway, we need to watch for specific signals. Mission updates indicating trajectory correction maneuvers, modifications to the peri-Jove timeline, or other planning activities. Since spacecraft retargeting takes months of preparation, any movement toward an intercept needs to be initiated soon. Additional clues include updates on propellant reserves and engine health from the Juno team. If they release information indicating readiness, that's a strong sign of serious consideration. Public advocacy from major scientific organizations like the American Astronomical Society's Division for Planetary Sciences can also exert pressure, nudging NASA toward action. But even if the Juno mission does not intercept 3IATLAS, other options remain. The United States Jupiter Icy Moon Explorer, or Juno's successor, the JUICE mission, launched in 2023, is en route to Jupiter and will arrive around 2030. Unfortunately, that timing is too late to intercept this particular object, which will have left our vicinity by then. Still, other missions could be devised, small, fast, lightweight probes tailored for interstellar encounters. The technology for such missions exists. The question hinges on political will and funding priorities. The ongoing debate over intercepting 3IATLAS exemplifies how science and politics are intertwined. The Juno intercept proposal serves as a case study, showing how scientific feasibility, resource considerations, and political interest collide. It demonstrates that humanity has the capability to undertake extraordinary missions when the will aligns. For now, Juno continues its dedicated exploration of Jupiter, while 3I-ATLAS advances on its inbound trajectory, with the clock ticking toward what will be the critical moment, the upcoming solar conjunction. This period, during which the upcoming period, often referred to as the blackout, marks a critical window in our observation of 3I-ATLAS, an interval when Earth's view of this extraordinary interstellar visitor will go completely dark. During this silence, an unseen gap, potentially pivotal developments could unfold, altering our understanding of what we're witnessing. This phase, which we can think of as the solar eclipse window, is like standing in a shadowed room, watching a mysterious figure approach a corner. Just as the individual nears the bend, the lights unexpectedly go out. You hear footsteps, perhaps the faint creak of a floorboard, and then silence. When the illumination returns moments later, the figure is in a slightly different position. Did they deliberately move? Did they perform some unseen action in the darkness? Or did they simply walk to their new spot naturally, with the darkness being incidental? This analogy captures the essence of what we are about to face with 3I-ATLAS. Let's carefully construct the timeline of this event, because the geometry of solar conjunction, when the sun blocks our line of sight, is the key factor here. Starting in late October of 2025, likely around the 25th, the angular separation between 3I-ATLAS and the Sun, when viewed from Earth, will decrease to less than roughly 50 degrees. This is a crucial threshold because it coincides with the Sun avoidance limit of the Hubble Space Telescope. Hubble cannot point its instruments near the Sun without risking damage from intense heat and radiation. Consequently, as the object approaches this proximity, Hubble will cease observations, effectively going dark on this target. By the time we reach October 29th, designated as perihelion day, the comet will be aligned directly between Earth and the Sun in terms of ecliptic longitude. Not perfectly aligned in an eclipse-like event, but close enough that the Sun's overwhelming glare will obscure the object from optical telescopes on the ground. During this period, which extends into late November, all Earth-based optical and near-infrared observations will be impossible. The Sun's brightness will drown out any signals from 3I-ATLAS. The precise moment when observations can again be attempted depends on the Sun-object-Earth angle widening beyond the safe viewing threshold, a process that takes time as the object moves away from the Sun's glare. According to official statements from the European Space Agency, the re-emergence window is expected to be in late November, roughly 4 weeks after the initial blackout begins. During this interval, these 4 weeks, the most intriguing interstellar object we've tracked so far will be completely hidden from Earth's view. This constitutes a significant observational gap, one that could conceal critical actions or changes. Now, considering what we will and won't be able to see during this period, it's essential to understand the limitations. We will lose access to visible and near-infrared photometry, meaning no brightness measurements, no tracking of outgassing activity, no continuous light curves, and no spectral data to analyze composition. Without the spectra, we cannot monitor the changing ratio of carbon dioxide to water, nor can we detect the emergence of ion emission lines or any new molecular species in the coma. Additionally, the absence of positional data will prevent us from refining the orbital model. Any non-gravitational acceleration, such as thrust or other forces, acting on the object during this time could go unnoticed. We would only discover such accelerations after the fact, by analyzing discrepancies in the object's position once observations resume. Furthermore, detailed structural insights, such as the shape of the nucleus or morphology of the coma, will be inaccessible during the deep blackout. We won't be able to resolve small features or observe any morphological changes that might occur in the interim. However, some indirect observations might still be possible. For instance, Mars orbiters, namely Mars Express and the Trace Gas Orbiter, have windows around October 3rd prior to the full onset of conjunction. These spacecraft could potentially gather data about 3IATLAS during that early window. Although their instruments are primarily designed for Mars science, they could, in theory, detect signals or features related to the comet if it is venting or emitting in ways detectable from their vantage point. Any data collected would be transmitted back to Earth and analyzed afterward. But it would be early in the conjunction period, not during the deep blackout itself. In essence, during this silent interval, our direct observational capabilities will be severely limited. We will be unable to track changes in brightness, composition, or position in real time. We will be effectively blind to any activity, be it natural outgassing, potential maneuvers, or even deliberate actions, during these critical weeks. This deliberate silence, whether caused by the geometry of the sun's obstruction or by strategic choice, introduces an unavoidable uncertainty. When the object reappears, the data we collect will be our first post-conjunction clues, potentially revealing whether it behaved as a natural comet or something more engineered. This phase underscores the importance of timing and the limitations. The James Webb Space Telescope, JWST, is strategically positioned at the L2 Lagrange point, approximately 1.5 million kilometers from Earth, on the side opposite the Sun. Its location offers a stable vantage point for deep space observations, but it also comes with specific limitations. Central to these constraints is JWST's Sun Shield, a vast, sophisticated shield designed to protect its sensitive instruments from the intense heat and radiation of the Sun. While this sun shield successfully maintains JWST's cryogenic environment, it also prevents the telescope from directly observing objects in the direction of the Sun. As a result, JWST cannot look straight toward the Sun or objects very close to it in the sky. However, depending on the exact position of an object along its orbit, specifically its ecliptic latitude, and considering JWST's own orbital parameters and orientation, there might be narrow geometric windows during which the telescope could potentially observe an object such as 3IATLAS during its conjunction with the Sun. These windows, though, would be extremely brief and far from ideal. They would only offer limited opportunities, with the object perhaps barely within JWST's field of view, and in a position that is not optimal for detailed analysis. Therefore, during the period when 3IATLAS passes behind the Sun from Earth's perspective, what is known as the conjunction or blackout period, reliable data collection by JWST is unlikely. Don't bank on JWST providing meaningful observations during that time. Moving beyond space-based telescopes, we also consider the capabilities of solar observatories like the Solar and Heliospheric Observatory, SOHO. SOHO is equipped with instruments called coronagraphs, specialized devices that block out the bright disk of the Sun itself, allowing scientists to study the Sun's extended corona, a glowing halo of plasma and magnetic activity around the star. These coronagraphs are also capable of detecting objects passing very close to the Sun, such as sun-grazing comets that venture into the Sun's immediate environment. However, in the case of 3IATLAS, its perihelion, the closest point to the Sun, occurs at about 0.9 astronomical units, a distance that is comfortably outside the field of view of most coronagraphs. The field of view of instruments like SOHO's coronagraphs generally covers regions very close to the solar limb, but not as far out as 0.9 AU. Consequently, there will be no data or direct observations of 3IATLAS during its perihelion passage from SOHO or similar solar observatories. Now, considering the realm of classified sensors, the picture becomes more speculative. The United States Department of Defense operates a network of space-based infrared early warning satellites, part of the Space-Based Infrared System, or SBRs, that are primarily designed to detect missile launches and other thermal signatures in space. These satellites are highly sensitive to heat emissions, capable of detecting sudden thermal changes with precision. If in the midst of its conjunction or during perihelion, 3IATLAS were to fire a large hot thruster, perhaps to adjust its course or perform maneuvers, these sensors might detect the resulting infrared flash. Such a signal could potentially be recorded even if ground-based telescopes are unable to see the object directly due to the sun's glare. But whether this data would be made available to the public or scientific community is another matter entirely. Classified systems are protected by national security protocols, and their data is generally kept secret. Nonetheless, history shows that information sometimes leaks or is published years later, through scientific papers, whistleblower disclosures, or covert channels. If something significant were to happen during conjunction, it's conceivable that indirect evidence might eventually surface, but only long after the fact. In summary, during the conjunction blackout period, our options for direct observation are severely limited. The continuous real-time monitoring we relied on before the event, such as from ground-based telescopes, JWST, or unclassified space-based sensors, becomes impossible or highly restricted. The best we can do is consider the scenarios that might unfold during this unseen window. Scenario 1. Nothing unusual occurs. The object continues its predicted trajectory, outgassing as a typical comet would, with no unexpected maneuvers or anomalies. When it re-emerges, perhaps late November, its position aligns with predictions based solely on gravitational effects, and its brightness and spectral features follow the expected evolution. Water vapor increasing, CO2 ratios decreasing, and emission lines appearing in a manner consistent with natural heating processes. In this case, the blackout period remains an unremarkable interval, and the silence holds no secrets. Scenario 2. Subtle maneuvering. The object performs a minor course correction during conjunction, perhaps a small delta V burn, just a few meters per second. Such a maneuver could be enough to slightly alter its trajectory but might be disguised as natural outgassing activity. When observations resume, astronomers might detect small residual discrepancies in its position, borderline at the limits of measurement accuracy. Leading, are these fragments the natural remnants of a comet's disintegration? Or are they deliberately deployed objects, probes or devices placed purposefully within the environment? Without witnessing the actual event itself, it remains challenging to determine with certainty. One possible scenario, which we might call Scenario 4, involves a significant transformation of the object's structure. Perhaps the nucleus has undergone a dramatic change. Maybe it has split into pieces, or perhaps a surface layer has peeled away, revealing a different internal composition. Alternatively, something could have unfolded in a way that alters its appearance. When imaging resumes after this event, the object might look markedly different. Its shape could be altered, its brightness distribution shifted, and its overall morphology changed. It's important to note that natural comets do occasionally split or fragment as a result of thermal stresses, tidal forces, or internal pressures. Thus, a change like this alone wouldn't definitively prove artificiality. However, if this structural change is accompanied by other anomalies, such as unusual chemistry or unexpected emissions, it would certainly raise compelling questions. Another plausible scenario, which we can label Scenario 5, involves the object actively emitting signals during the period of solar conjunction. For instance, it might begin broadcasting a narrowband radio transmission or modulated light signals, something intentionally designed perhaps for communication or signaling purposes. Because of the sun's glare and proximity, ground-based telescopes on Earth would be unable to detect such signals during conjunction. However, spacecraft positioned elsewhere in the solar system, such as orbiters around Mars, lunar satellites, or deep space probes, might have the capability to pick up these signals. By the time Earth-based telescopes are able to reacquire the object, the emission would likely have ceased, leaving us with second-hand reports and fragmented data from those remote sensors. Each of these scenarios, natural fragments from breakup, structural reconfiguration, or active signaling, is within the realm of possibility, though some are more probable than others. The default assumption, or scenario 1, remains that of a natural object behaving within expected parameters. Scenarios 2 through 5, however, involve increasingly extraordinary phenomena. Anomalies that would suggest something unusual is occurring, potentially hinting at artificial origins or covert activity. What's critical to grasp here is that the absence of continuous observation during the solar conjunction creates a significant gap in the data. If any anomalies or unusual behaviors manifest during this period, we simply won't have direct evidence of their occurrence. We will have only the before and after snapshots, what was observed prior to conjunction and what is observed afterward, without any record of what transpired during the blackout. This makes drawing definitive conclusions particularly difficult, as the timing of any potential maneuvers or events will remain uncertain. This conjunctive period is technically the perfect window for maneuvering if the goal was to avoid detection, whether for natural reasons or for a deliberately engineered purpose. Conversely, it could also be seen as an unfortunate coincidence of geometry, if the object is simply a natural comet passing through the solar system. History provides several examples of important events coinciding with solar conjunctions, adding context to our current situation. Take, for example, the Mars Pathfinder mission of 1997. During its solar conjunction, the lander and rover entered safe mode, ceasing data transmission. When contact was re-established, everything appeared to be fine, but the period of silence was a source of uncertainty. Similarly, in 2020, the Voyager 2 spacecraft experienced a loss of telemetry during its conjunction period, forcing engineers to troubleshoot blindly using stored commands and predictions. An experience marked by tense moments until communication was restored. In the case of Comet Ison in 2013, a sun-grazing comet passed behind the Sun and disintegrated during perihelion. We observed it as it went in, but it disappeared during the closest approach, and when it should have emerged, it was gone. The breakup occurred during the blackout, and we could only infer what happened, never witnessing the event directly. In each of these cases, the conjunction added an element of drama and uncertainty. The case of Ison in particular demonstrated how a critical event can be entirely concealed by the sun's glare, with the true nature of the event only understood afterward. What should we anticipate with 3IATLAS? The answer hinges on the observations made after the conjunction period. If the follow-up data reveal that everything appears normal, no structural changes, no unexpected emissions, and a consistent trajectory, we can breathe a sigh of relief, or perhaps a note of disappointment depending on one's perspective. We simply move forward, considering it a strange but natural comet passing through our solar neighborhood. However, if the post-conjunction observations reveal anomalies, such as shifts in position, unexpected chemistry, or new structural features, the implications deepen significantly. We would then need to scramble to determine precisely what occurred during the conjunction period and when. The silence before the sun's glare is already upon us. The countdown has begun, and once the sun's glare lifts, revealing the objects, even as the sun's glare plunges our view into silence, unseen eyes may continue to watch. Instruments we neither control nor access operate silently in the shadows, their observations hidden from us. The pressing question is whether these clandestine watchers will ever reveal what they see. This is the essence of Part 12, Hidden Eyes, encompassing the efforts of ESA, JWS, and other classified sensors. When I mention that we are blind during a solar conjunction, I refer to the perspective of the public, the scientific community operating through open channels and civilian space agencies that share their data freely. Yet in this modern age, the term blind is relative. There are other eyes, some known, some hidden, that keep vigil without our knowledge. Let's begin with those we are aware of. The European Space Agency maintains 2 active spacecraft near Mars, Mars Express, which has been orbiting since 2003, and the Trace Gas Orbiter, or TGO, which arrived in 2016. Both are primarily tasked with studying Mars, mapping its surface, analyzing its atmosphere, and searching for trace gases like methane that could hint at biological or geological activity. However, these spacecraft are equipped with instruments capable of being pointed elsewhere, and ESA has confirmed that both will attempt observations of the interstellar object known as 3IATLAS around October 3, 2025, when the comet passes within approximately 30 million kilometers of Mars. This encounter occurs before the full solar conjunction blackout, providing a window of opportunity to gather data. The significance lies in the fact that Mars occupies a different position in space than Earth, offering a distinct viewing geometry. What exactly can Mars Express and TGO see during this window? Mars Express is equipped with the HRSC, the high-resolution stereo camera capable of imaging in wavelengths beyond visible light. It can capture images in the infrared and ultraviolet spectra, providing detailed surface and atmospheric data. Additionally, the Omega spectrometer can detect emissions from molecules such as carbon dioxide, water vapor, and dust within the comet's coma. Although at such a distance, the resolution of HRSC will be limited and the images may be blurry, but they could still reveal the overall structure of the comet's activity. TGO, meanwhile, carries instruments like NOMAD and ACS, spectrometers designed to analyze Mars' atmosphere. Yet these are sensitive enough that should the comet emit strong enough signals, they could detect the volatile gases escaping from 3IATLAS. TGO also has a multispectral imaging system capable of capturing wide-field views of the comet's coma, potentially revealing asymmetries or jets of outgassing. ESA has been cautious in setting expectations, clarifying that these are not dedicated comet-hunting missions. They are Mars orbiters temporarily repurposed to try and observe an interstellar visitor. The data they gather will likely be marginal, difficult to interpret, and limited in detail. Still, even marginal data can be valuable. However, there's an important caveat. These observations will be subject to data embargoes. The science teams will analyze, interpret, and publish their findings in due course, which could mean several months before any results reach the public domain. Therefore, even if Mars Express and TGO capture something noteworthy on October 3rd, we might not learn about it until early 2026. Beyond ESA, other potential eyes may also be attempting distant observation. The European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, launched in April of 2023, is currently in transit, cruising through the inner solar system en route to Jupiter. Its trajectory and timing might allow a distant glimpse of 3IATLAS during the Earth's solar blackout period, particularly in November 2025. However, JUICE is positioned millions of kilometers from the comet, and its instruments are primarily designed for close-up studies of Jupiter's moons, not for remote observation of passing comets. Given its current mission profile and distance, the likelihood of meaningful data is limited. If it does attempt such observations, the results will probably be sparse and not immediately available, with official reports likely delayed until February 2026. In the broader picture, these known efforts are just the tip of the iceberg. Numerous classified sensors, operated by military and intelligence agencies, stand vigil in the shadows, their capabilities and observations concealed from the public eye. These systems, including advanced infrared and optical observatories, are optimized to detect missile launches, satellite maneuvers, and other threats to national security. Their data, by design, remains classified. Could these covert sensors detect 3IATLAS during the solar conjunction blackout? It's plausible. Many of these sensors monitor infrared signatures capable of spotting thermal anomalies, such as a spacecraft firing its engines or venting heat. If the object were to perform a significant maneuver, firing a thruster or deploying secondary objects, these sensors might record an infrared flash, even if ground-based telescopes cannot see it. Yet, whether this data is shared with the public is another matter. The Department of Defense, the European Space Agency, has made it clear that the findings from the upcoming observations of the JUICE spacecraft, should they occur, might not be accessible to the public until February of 2026. This means that the space agency's information, especially concerning this object, will be few, far away, and slow to reach the wider scientific community or the public. Meanwhile, there exists a realm of observation that operates beyond the reach of open science and civilian agencies, an unseen, heavily classified domain. The United States in particular maintains an extensive network of covert space surveillance assets. Some of these are optical telescopes designed primarily to monitor and track satellites and space debris in Earth's orbit, an ever-present watchtower for space traffic management and national security. Others are infrared sensors calibrated to detect the intense heat signatures of missile launches, nuclear tests, or other clandestine activities. Collectively, these systems form what is known as the Space Surveillance Network, or SSN, a highly sophisticated, highly capable set of tools that excel at their designated missions. The question naturally arises: could these secretive, highly sensitive systems detect the interstellar object known as 3IATLAS during its solar conjunction when it slips behind the Sun from our vantage point? The infrared early warning satellites, such as the legacy systems like ESPERS and their predecessors, have a very specific function. They are optimized to identify the bright, hot plumes of rocket engines igniting or burning during launches. A comet nucleus, at roughly 1 astronomical unit from the Sun, is indeed warm, but not because of active propulsion. Its infrared glow results from solar heating. Unlike a rocket, it doesn't produce a sudden, intense thermal spike. It radiates heat steadily. Therefore, the passive detection of such a comet by these sensors is unlikely unless something extraordinary occurs, such as the object firing a thruster or engaging in some form of propulsion that produces a distinct infrared signature. If 3IATLAS were to ignite a chemical rocket during the conjunction, the resulting infrared flash would be prominent against the background. The sensors would undoubtedly pick up such an anomaly. But here's the critical question: would we, the public or the civilian scientific community, ever learn of such an event? That depends entirely on policies governing classified information. The data collected by ESPERS and similar systems is highly classified. Their capabilities, the precise locations, and the pointing directions of these satellites are kept secret for national security reasons. The Department of Defense does not routinely share this information with civilian scientists, nor is it published in open literature or astronomical journals. However, history provides some context. Leaks happen. Information that is initially classified can, over time, surface publicly, sometimes years later, when the data is declassified for scientific purposes. During the Cold War, for example, the U.S. Air Force's satellites detected meteor impacts and fireballs, which later contributed to our scientific understanding of high-altitude phenomena. These instances set a precedent. If a major anomaly or indication of artificial activity were detected by classified sensors, there is a possibility, albeit not a certainty, that the information could eventually leak out. Most likely, such revelations would not happen in real time. The flow of classified information is slow, deliberate, and carefully managed. Only in cases of significant, undeniable anomalies, those that might suggest a breach of security or potential threat, would there be a push to declassify and release information promptly. But even then, the process would involve rigorous verification and approval. Turning to the James Webb Space Telescope, the JWST, the story becomes more nuanced. As previously discussed, JWST's orbit at the L2 Lagrange point, approximately 1.5 million kilometers from Earth on the side opposite the Sun, imposes strict constraints on its observational capabilities. Its sunshield, designed to maintain the cryogenic temperatures of its instruments, permanently blocks its line of sight toward the Sun, and by extension most objects very close to the Sun's position in the sky. This means that JWST can never directly observe the object during the solar conjunction because the Sun's glare and the spacecraft's orientation restrictions prevent it. Its field of regard, a conical region of the sky that the telescope can scan, avoids the Sun by at least about 85 degrees at all times. Yet the dynamic nature of the solar system's geometry complicates matters. As Earth orbits the Sun, and as L2 maintains its position relative to Earth, the relative positions of the Sun, Earth, JWST, and the interstellar object shift continuously. Depending on the comet's orbit, its ecliptic latitude, and the specific phase of its trajectory, there might be fleeting windows during which JWST's field of regard could include the position of 3IATLAS, even during the period of solar conjunction. Such a window would require precise alignment, an intersection of the object's position, JWST's orbit, and the Sun avoidance constraints, and would likely be very brief. In practice, this geometric complexity means that direct observation of the object during conjunction is the likelihood of the James Webb Space Telescope capturing valuable data during the upcoming conjunction hinges on several factors, including the comet's ecliptic latitude, its precise position along the ecliptic longitude, JWST's current orbital phase, and the Sun avoidance angle, parameters that collectively determine whether a window exists for observation. Without running detailed calculations, I cannot definitively specify where or when this window might occur. However, the possibility remains. Should JWST manage to observe the comet during this critical period, the scientific yield would be extraordinary. Its spectroscopic instruments, unparalleled in their sensitivity and resolution, could accurately determine the ratio of carbon dioxide to water, detect trace molecules that provide clues about its composition, and map the temperature distribution across the coma, revealing details that are impossible to resolve from Earth-based telescopes alone. Yet it's important to recognize that JWST's observing time is highly competitive, so much so that it's the most oversubscribed telescope in history. Securing a slot requires submitting a rigorous proposal well in advance, often months before the observation window, or requesting discretionary time for urgent targets of opportunity. As of now, it remains uncertain whether anyone has formally submitted such a proposal to observe the comet during conjunction, since this information is typically kept confidential until after the data collection and publication phases. The key question then becomes, might JWST observe during this period? The answer is possibly. But will we know immediately? Likely not. The broader issue at play is that the silence in data during conjunction may be a policy decision, an intentional choice to withhold information rather than a mere technical limitation. If something anomalous or unexpected is detected by Mars orbiters, JWST, or classified sensors operating in the background, the decision to disclose that information immediately, delay it for further analysis, or keep it classified altogether depends on human judgment and strategic considerations, not on the laws of physics. All scientific data undergoes a process: initial validation, peer review and coordinated release before it becomes publicly accessible. Space agencies typically do not broadcast raw observations on social media. Instead, they analyze, verify, and then formally announce their findings. Military and intelligence agencies operate under different protocols, often involving classification and compartmentalization, revealing only what's deemed strategically necessary or legally obligatory. Therefore, if the comet behaves in an unusual way during conjunction and is detected by these covert systems, the flow of information to the public could be delayed by weeks, months, or even indefinitely. This isn't a matter of conspiracy, but simply how information systems and national security protocols are designed. The core question for us as engaged observers is not whether some entity might observe phenomena we cannot see, but whether they will choose to share that information. Our best course of action is to focus on the open data streams. When the comet reemerges in late November, we should monitor for position measurements from amateur astronomers and professional observatories worldwide. We should watch for spectral data indicating changes in its composition and listen for official announcements from the European Space Agency or NASA regarding measurements from Mars orbiters. We should also remain alert to any data releases from JWST or other facilities that might provide insight into the comet's properties. It's important not to overreact to the idea of secrecy. Most solar system science is conducted openly. The majority of valuable data comes from publicly accessible observatories, and classified sensors are primarily designed to track Earth-based threats such as missile launches or satellite maneuvers, not interstellar objects. The probability that classified systems hold unique, decisive information about this interstellar visitor is low, but it remains wise to stay vigilant. If, several months after conjunction, an unexpected paper surfaces, one containing data that could not have been obtained through public observatories, then it's essential to question and scrutinize the source of that information. In the end, the uncertainty surrounding the observation window during conjunction is a natural part of scientific investigation, an inherent challenge that emphasizes the importance of open data and careful analysis. Our role is to systematically track available signals, spectra, and positional data, and to remain cautious about jumping to conclusions based on incomplete information. Whether we find ourselves facing a natural anomaly or something more extraordinary, the key lies in patience, rigorous verification, and the recognition that many questions can only be answered once the comet reemerges from behind the sun's glare. If whispers from mission scientists suggest intriguing discoveries that have not yet been made public, it is essential to remain attentive. Information inevitably finds its way out. Leaks happen. The covert observers, the hidden eyes, are present, discreetly monitoring from afar. Whether they are observing at this very moment and whether they choose to reveal what they see remains a matter of time and circumstance. Thank you for spending your evening here. I trust you gained some new insights, and I look forward to our next discussion. Until then, good night.